What if everything you thought you knew about the universe, about the very stage upon which reality plays out, was just an illusion? What if the smooth, continuous expanse of space and time is not so smooth after all, but instead a turbulent, seething, and chaotic sea, constantly bubbling with energy at scales so unimaginably small they defy comprehension? This isn't just a wild thought experiment. This is the frontier of our understanding, the mind-bending domain of the universe's quantum foam. At this most fundamental level, the fabric of reality itself is thought to be a frothing ocean where virtual particles spontaneously blink into and out of existence, borrowing energy from the void for fleeting moments before vanishing back into nothingness. It's a realm where the classical laws of physics we take for granted break down completely, replaced by a bizarre and probabilistic dance that challenges our very perception of what is real. This is the universe's deepest secret, hidden in plain sight, and it's more strange and wonderful than anything we could have dreamed up. Today, we're embarking on an epic adventure to explore this astonishing concept. We're going to dive headfirst into the quantum foam, navigating 30 of the most incredible, thought-provoking, and downright revolutionary theories that scientists have proposed to explain its nature. This journey will take us from the very birth of the cosmos to the distant future of the universe, connecting the impossibly small with the unimaginably large. We'll see how this foamy foundation might hold the key to unifying gravity with quantum mechanics, how it could be the source of dark energy, and how it might even allow for phenomena that sound like pure science fiction, like microscopic wormholes and warp drives. This isn't a dry academic lecture. This is an exploration of the greatest mystery show in the cosmos, and you have a front row seat, so get ready to have your mind expanded. We're about to peel back the curtain on reality and look at the scaffolding that holds it all together. This is a story of human curiosity, of our relentless drive to understand the universe not just as it appears, but as it truly is in its most raw and fundamental form. From the brilliant minds who first conceived of this quantum frenzy to the modern theorists pushing the boundaries of knowledge, we're going to uncover why this tiny, turbulent world is the most important thing you've probably never heard of. Let's begin our descent into the foam. Our journey into the quantum foam begins with the first and most foundational theory, the startling revelation that spacetime itself is not a smooth, continuous stage, but a turbulent quantum fluctuation. For centuries, we imagined the vacuum of space as a true void, an empty nothingness where particles move through passive emptiness. But quantum physics tears down this classical picture entirely. At the very smallest scales, at a level known as the Planck length, the fabric of reality is anything but calm. It's a seething, effervescent sea where the very concepts of here and now lose their meaning. This frenetic activity is the universe's quantum foam, a frothing foundation where tiny wormholes and loops of spacetime may constantly form and dissolve in a probabilistic frenzy. The engine behind this perpetual foaminess is the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle tells us that on these minute scales, energy can be borrowed from the void, leading to spontaneous eruptions of virtual particle-antiparticle pairs. These particles aren't just appearing, they are manifestations of the foam itself, popping into existence for impossibly brief moments before annihilating each other and returning the energy back to the vacuum. This isn't a peaceful process. It's a violent, chaotic churn where the geometry of spacetime is constantly being roiled and reshaped. Think of a perfectly calm body of water. On the surface, it looks serene and unbroken. But if you could shrink down to the size of a molecule, you'd see a frantic dance of jostling water molecules, constantly colliding and vibrating. The quantum foam is like that, but for spacetime itself. The smooth continuum we experience is just an average, a large-scale illusion created by our inability to perceive this unimaginably tiny, turbulent reality. This foundational theory completely upends our understanding of nothing. Empty space is not empty, it is the most active, dynamic, and energetic thing we can possibly conceive. Building directly from that foamy foundation where spacetime itself is in a state of constant, turbulent flux, we come to a theory that sounds like it's been pulled straight from the pages of a science fiction novel, yet is a serious proposal from some of the brightest minds in theoretical physics. This is the idea that the quantum foam isn't just a chaotic froth of energy, but is in fact riddled with an unimaginable number of microscopic wormholes. Picture this: at every single point in the space around you, at a scale a billion times smaller than an atom, countless tunnels are constantly blinking into and out of existence, stitching the fabric of reality together in an intricate, ever-changing web. These aren't the stable, spaceship-sized wormholes of interstellar travel dreams. They are evanescent structures forming when the fluctuating geometry of the foam momentarily pinches off and creates a bridge, a shortcut between two otherwise separate points in spacetime. The potential implications of such a phenomenon are staggering to contemplate. For one, these fleeting tunnels could provide a stunningly simple physical explanation for one of quantum mechanics' most enduring mysteries: quantum entanglement. That's the bizarre phenomenon where two particles, even when separated by vast distances, remain inextricably linked, with the state of one instantly influencing the state of the other. Einstein famously derided this as spooky action at a distance, because it seemed to violate the cosmic speed limit set by light. But what if there is no spooky action across a distance? What if, at the very moment we measure one particle, our observation is transmitted through one of these microscopic wormholes in the foam, connecting the particles through a shortcut that bypasses conventional space entirely? In this view, the universe at its most fundamental level is so thoroughly interconnected by this foamy network of tunnels that true separation is an illusion. Everything is subtly tied to everything else through this hidden plumbing of reality. And if these wormholes can connect different points in space, why not different points in time as well? The transient nature of these structures opens up the speculative possibility that they could link not just different wheres but different whens. A microscopic wormhole could, in theory, connect a moment in the present with a moment in the past or future. While the practical challenges of utilizing such a phenomenon for time travel are unimaginably vast, these wormholes are thought to be smaller than subatomic particles and exist for fractions of a second. The theoretical possibility forces us to confront profound questions about causality and the nature of time itself. It suggests that the linear flow of time we experience might be a large-scale averaging effect, and that at the quantum level, the past, present, and future could be far more intimately connected than we ever realized. Of course, the very thing that makes this theory so compelling is also what keeps it firmly in the realm of the theoretical for now: the incredible instability of these structures. The same quantum fluctuations that give birth to a wormhole also supply the energy that violently rips it apart almost instantly. It's like a soap bubble forming on the surface of a turbulent sea. It might achieve a perfect, beautiful form for a single, fleeting moment before the very forces that created it cause it to violently pop. The energy required to stabilize even one of these microscopic passages, to pry it open and keep it from collapsing, is thought to be astronomical, requiring a form of matter with negative energy density, something we have yet to discover or create. So, while the quantum foam may be a seething cauldron of potential shortcuts through the cosmos, it's a bustling terminal where tunnels are constantly being built and demolished, offering no stable route for anything larger than the most fundamental of particles to traverse. Now, if the idea of spacetime being a frothing sea of wormholes seems radical, prepare for a theory that challenges the very nature of dimensionality itself. This brings us to the holographic principle, a concept so profound it suggests that our entire three-dimensional universe, with all its galaxies, stars, planets, and even you and me, might be nothing more than a magnificent projection, a cosmic hologram. And the quantum foam, it could be the very static, the granular noise of that projection. Imagine a movie played on a vast screen. The images appear to have depth and volume, but all the information needed to create that three-dimensional illusion is actually encoded on the two-dimensional surface of the screen itself. The holographic principle applies this same logic to the cosmos. It posits that all the information describing everything within a volume of space, every particle, every force, every event, is actually stored on a distant, bounding surface, a two-dimensional membrane that encloses it. Our rich, three-dimensional reality is just a projection from that data. So, where does the quantum foam fit into this incredible picture? If our universe is a hologram, then the smooth, continuous spacetime we perceive is an illusion, just like the smooth image on a television screen. Get close enough to that screen, and you'll see it's actually made of individual, discrete pixels. The holographic principle suggests that the frantic, flickering nature of the quantum foam is the fundamental pixelation of spacetime. Each fluctuation, each virtual particle pair blinking in and out of existence could be a single pixel in the cosmic projection, a tiny unit of information on the universal screen. The foam's chaotic churn is the underlying data processing that manifests as the reality we experience. This provides a stunningly elegant potential link between gravity and quantum mechanics, two pillars of physics that have stubbornly resisted unification. Gravity, in this view, might not be a fundamental force at all, but rather an emergent phenomenon. Just as the temperature of a gas emerges from the collective motion of countless molecules, the force of gravity could emerge from the complex interactions and information exchanges happening within this holographic foam at the Planck scale. The way the foam's structure twists and contorts could directly encode the gravitational field we feel, tying the large-scale geometry of the universe directly to the tiny, informational bits of the quantum world. This is a truly revolutionary way of seeing the cosmos, where the most fundamental ingredients aren't particles or forces, but information itself. The universe is computed into existence, and the quantum foam is the visual evidence of that computation at work, a constant reminder that we are living in a projected reality of breathtaking complexity and depth. This foundational churn of the quantum foam, this endless creation and destruction of virtual particles, isn't just a curious side effect of quantum mechanics. It contains an immense amount of energy. And this brings us to one of the most compelling and perplexing theories in modern cosmology, the possibility that the quantum foam itself is the source of dark energy, the mysterious force driving the accelerated expansion of our universe. For decades, astronomers have known that not only is the cosmos expanding, but that expansion is speeding up. Something is counteracting the relentless pull of gravity, pushing galaxies apart at an ever-increasing rate. This something is what we call dark energy, and it constitutes about 68% of the entire universe. Yet, its origin has remained one of the greatest unsolved mysteries in physics. The quantum foam offers a tantalizing solution. Every cubic centimeter of what we perceive as empty space is, according to quantum field theory, a turbulent sea of virtual particle pairs flickering in and out of existence. This activity isn't free. It contributes to what's known as the vacuum energy density, a background energy inherent to space itself. This energy, it turns out, has a bizarre property predicted by Einstein's theory of general relativity. It generates a repulsive form of gravity. While matter and energy normally create an attractive gravitational force that pulls things together, a positive energy density with a certain type of negative pressure, exactly the kind associated with the quantum vacuum, produces a gravitational push. So, the ceaseless activity of the foam could be providing the very anti-gravity force that is inflating the entire cosmos. imagine the universe as a vast loaf of raisin bread baking in an oven. The raisins are galaxies. Now imagine that the dough itself is the quantum foam. As the bread bakes, the dough doesn't just expand, it actively rises, pushing the raisins farther and farther apart at an accelerating rate. In this analogy, the yeast causing the dough to rise is the relentless energy of the quantum foam. It's not a force acting from outside the universe, but an innate property of the space between everything. There is, however, a monumental problem with this beautifully simple idea. A problem so severe that it's often called the worst theoretical prediction in the history of physics. This is the cosmological constant problem. When physicists attempt to calculate the expected energy density of the quantum foam by summing up all the contributions from every possible quantum fluctuation, the number they get is astronomically, unimaginably large. We're talking about a value that is 1 followed by 120 zeros larger than the energy density we actually observe from the effects of dark energy. If the vacuum energy were really that immense, the repulsive gravity it generated would have been so powerful that it would have torn every atom, every nucleus, every fundamental particle in the universe apart within a fraction of a second after the Big Bang. Galaxies, stars, planets, and life would never have had a chance to form. The fact that we exist to observe a relatively sedately expanding universe means that the actual value of this vacuum energy is incredibly small, almost but not quite zero. This discrepancy between the theoretical calculation and the observational reality is a crisis at the heart of modern physics. It tells us that our understanding of the quantum vacuum is profoundly incomplete. Perhaps the wildly fluctuating positive and negative energies in the foam cancel each other out to a far greater degree than we currently understand, leaving only a tiny leftover residue that we measure as dark energy. Or maybe the holographic principle plays a role, with the information content of spacetime placing a fundamental limit on how much energy can be stored in the vacuum. Whatever the solution, the cosmological constant problem highlights a fundamental gap in our knowledge, a glaring signpost that a deeper theory of quantum gravity is needed to truly reconcile the frantic micro-world of the foam with the serene macro-world of the expanding cosmos. So, while the quantum foam remains a prime suspect for the origin of dark energy, the case is far from closed, and the mystery of why the universe is as gentle as it is remains one of its most profound enigmas. While we've been exploring the quantum foam as a turbulent, fluctuating sea, another grand theory in physics offers a radically different yet equally profound picture. This is the perspective of loop quantum gravity, or LQG, which proposes that spacetime isn't just frenetically active, it's actually granular, woven together from individual, discrete building blocks. Imagine the fabric of the cosmos not as a smooth, infinitely divisible sheet, but as a magnificent tapestry. In this tapestry, each individual thread, each tiny loop, represents a fundamental, indivisible atom of space. These are not atoms in the traditional sense of chemistry. They are the absolute smallest possible units of volume existing at the Planck scale. According to LQG, you cannot have half of one of these space atoms, just as you cannot have half a photon of light. This granular, quantized structure is the quantum foam. The frantic, foamy appearance we've discussed is the manifestation of this underlying atomic geometry, a dynamic network where these tiny loops of space constantly interact and reconnect. This idea of a discrete spacetime has a monumental consequence, one that tackles one of the most troubling concepts in all of physics, the singularity. In Einstein's theory of general relativity, singularities are points of infinite density and zero volume, places where the known laws of physics completely break down. They lurk at the center of black holes and are thought to be the starting point of the Big Bang. Infinities in physics are generally a sign that our theory is incomplete, that we're missing a crucial piece of the puzzle. Loop quantum gravity directly resolves this by its very nature. Because space is made of finite, minuscule atoms, it simply cannot be compressed into an infinitely small point. Think of it like a piece of fabric. You can crumple a silk sheet into a very small ball, but it will still have a finite density. In the LQG universe, as matter collapses under its own gravity to form a black hole, or as we rewind time to the universe's birth, the density and curvature of spacetime reach an enormous maximum, but then they hit a fundamental limit. The atoms of space resist further compression, and the physics actually bounces rather than breaking down. This leads to the stunning possibility that the Big Bang was not a singular creation from nothing, but a big bounce from a previous contracting phase of the cosmos. Similarly, the heart of a black hole might not be a point of infinite doom, but a gateway to another region of spacetime or a different universe entirely. The geometry that emerges from this is not a random froth, but an intricate, woven structure often called a spin network. Picture a vast cosmic mesh, a web of connections where each intersection is a tiny volume of space and each link represents a quantum of area. This network isn't static, it evolves over time with its connections changing and updating, which is what gives rise to the dynamic fabric of spacetime we experience. The smooth, continuous space and time we move through in our daily lives is an large-scale illusion born from this incredibly fine-grained, pixelated reality. Much like a digital photograph appears smooth from a distance but reveals its pixels when you zoom in. This perspective provides a beautiful resolution to the infinities that plague classical gravity and offers a compelling, visualizable model for the quantum foam. It's not merely a chaotic sea of energy, but a highly structured, quantized architecture, the true atomic foundation of our universe. Now we shift our perspective from a woven fabric of space to something even more fundamental, a universe built not from things but from relationships. This is the domain of causal set theory, a framework that proposes the ultimate ingredients of reality are not points in space or even little loops, but discrete events connected by a single, powerful principle, cause and effect. Imagine the entire history of the cosmos from the Big Bang to this very moment, not as a movie playing out on a continuous screen, but as a vast, growing network of moments. Each event, a photon being emitted from a star, an electron changing its orbit in an atom, a thought forming in your mind, is a fundamental, indivisible element in this network. What gives this network its structure is not their position in space, but their order in time, specifically which events can influence which others. If one event can send a signal, even just a photon of light, to another event, then they are causally linked. The entire cosmic story is written in this web of cause and effect. In this view, the smooth, four-dimensional spacetime of Einstein's relativity is not a primary stage. It's a secondary, emergent phenomenon that arises from the collective pattern of countless causal connections. The geometry of space, the flow of time, even the force of gravity, are all shadows cast by this deeper, underlying network of events. So, where is the quantum foam in this austere causal picture? If spacetime is an emergent illusion, then the foam is the fundamental graininess of that illusion. The frantic, probabilistic flickering we associate with the quantum foam is a direct reflection of the discrete and probabilistic nature of the causal connections themselves. At the most fundamental level, the universe isn't deciding with certainty whether event A causes event B. There is a quantum probability associated with each potential link in the cosmic network. The foaminess is the manifestation of this underlying uncertainty in the causal structure. It's as if the universe is constantly deciding, moment by moment, how to weave its own causal tapestry, and the quantum foam is the statistical noise of that decision-making process. This provides a breathtakingly elegant way to unify the worlds of quantum mechanics and gravity. Gravity, in Einstein's theory, is the curvature of spacetime. In causal set theory, that curvature is not fundamental. It is a direct consequence of the number and arrangement of causal links between events. A dense cluster of events with a rich web of causal connections would manifest to us as a region of strong gravity, like the area around a black hole. A sparse region with fewer links would appear as nearly flat, empty space. The probabilistic nature of these links at the quantum scale is what gives rise to the fluctuating, foamy geometry we've been exploring. To grasp this, picture an enormous, dark auditorium. Imagine each member of the audience holds a single sparkler. Now, imagine they begin to light their sparklers, one after another, but not randomly. Each person lights theirs only after seeing the light from someone else's, a chain reaction of causality. From a distance, you wouldn't see the individual people or the precise moments of ignition. Instead, you would see waves of light spreading out, merging, and creating beautiful, complex patterns. The smooth, flowing waves of light are like our emergent spacetime. But the underlying reality is a discrete set of events, the ignition of each sparkler, connected by the causal chain of seeing and being seen. The quantum foam, in this analogy, would be the inherent unpredictability in the process. Maybe sometimes a sparkler fails to light the next one immediately, or maybe the light is seen by two people at once, creating a probabilistic branch in the chain. This underlying fuzziness in the causal connections is what creates the foamy texture in the emergent wave of light. Causal set theory gives us a universe that is, at its heart, a story of relationships. Nothing exists in isolation. Everything is defined by its connections to everything else. The quantum foam is not a separate entity, but the dynamic, probabilistic breath of the cosmic network itself, constantly redefining the causal order from which all of reality blossoms. But to truly grasp the magnitude of this challenge, we need to dive into the numbers, because the discrepancy isn't just large, it's arguably the most embarrassing failure of a theoretical prediction in all of modern science. Let's put it this way: when we calculate the expected vacuum energy density by summing up all the quantum fluctuations from every known field and particle, the result is a number so colossal it defies everyday comparison. It suggests that every single cubic centimeter of empty space should contain more energy than the entire observable universe appears to hold in the form of matter. If this were true, the repulsive gravitational force generated would have been so unimaginably powerful that the universe would have blown itself apart in the first instance of the Big Bang. Not a single atom, not a single star, not a single planet could have ever formed. The cosmos would be a near-empty, rapidly expanding void, utterly incapable of supporting life or structure. The fact that we are here, observing a universe filled with galaxies and stars, means that the actual, measured value of the vacuum energy is almost zero, but not quite. It's a tiny, positive number that is responsible for the gentle, accelerated expansion we see today. The problem is that our theoretical prediction is about 120 orders of magnitude too large. That's a 1 followed by 120 zeros. To try and comprehend that scale, consider that the total number of atoms in the entire observable universe is estimated to be around 1 followed by only 80 zeros. So the error in our vacuum energy calculation is a factor that is 10 billion times larger than the number of atoms in everything we can see. This isn't just being off by a little. This is a screaming signal that our most fundamental theories of the very small and the very large are missing a crucial piece of the puzzle. So, what are the potential solutions to this vacuum catastrophe? How can we reconcile this staggering disagreement? One prominent line of thinking involves the concept of supersymmetry. This elegant theory proposes that every known fundamental particle has a hidden, super-partner particle that we have yet to discover. For every electron, there would be a selectron, for every quark, a squark. The beauty of this idea, in the context of the vacuum energy, is that the quantum fluctuations of these superpartners would have the opposite sign to their normal matter counterparts. They would contribute a negative energy to the vacuum. In a perfectly unbroken supersymmetric universe, the positive and negative contributions from all these particle pairs would cancel each other out with exquisite precision, resulting in a net vacuum energy of exactly zero. This would solve the problem beautifully. However, we don't live in that perfect universe. If supersymmetry is real, it must be a broken symmetry, meaning these superpartner particles, if they exist, are incredibly heavy and have so far eluded our most powerful particle colliders. The cancellation would then be almost, but not perfectly, complete, potentially leaving behind the tiny, residual energy we observe as dark energy. While this is a compelling idea, the continued failure to find any direct evidence for supersymmetric particles has cast some doubt on this elegant solution. Another, more philosophical approach is known as the anthropic principle. This reasoning suggests that the value of the vacuum energy isn't determined by a fundamental law of physics that demands a specific number. Instead, it could be one of many possible values across a vast multiverse, a cosmic landscape of universes, each with its own physical constants. In the overwhelming majority of these universes, the vacuum energy would be far too large, leading to a rapid, sterile expansion where life is impossible. But in an incredibly rare subset, by pure chance, the value is small enough to allow galaxies to form and life to evolve. We, of course, find ourselves in one of those exceptionally rare, life-permitting universes, so we observe a value that seems miraculously fine-tuned for our existence. From this perspective, there is no deeper explanation. The vacuum energy is what it is because if it were any different, we wouldn't be here to ask the question. While this idea offers an explanation of sorts, it leaves many physicists unsatisfied as it moves the problem from the realm of predictive physics to one of cosmic chance. Other proposals are even more radical. Some theories suggest that the vacuum energy isn't a constant at all, but a dynamic field that has slowly decayed over the immense history of the cosmos from an initially enormous value to the small one we see today. Perhaps we are just living at the right time to witness its current low state. Others, drawing from the holographic principle we discussed earlier, argue that the amount of information that can be stored in any volume of space is fundamentally limited, which naturally caps the maximum possible vacuum energy and prevents it from reaching the catastrophically high values our naive calculations suggest. The vacuum catastrophe, therefore, is not just a single problem to be solved, but a profound gateway. It forces us to question the very nature of empty space, the relationship between quantum mechanics and gravity, and our place in the cosmos. It is a humbling reminder that for all our knowledge, the universe still holds deep mysteries that challenge the core of our understanding. Moving from the cosmic scale enigma of dark energy, we now turn our attention to a phenomenon that could offer us a tangible, measurable signal from the quantum foam itself. This is the fascinating proposal that the frothy texture of spacetime might not be perfectly uniform, and that this imperfection could leave a tiny fingerprint on the fastest thing in the universe, light. According to this theory, the speed of light in a vacuum, that fundamental constant c that underpins all of modern physics, might not be perfectly constant for all light. For photons of exceptionally high energy, those traveling from the most violent explosions in the cosmos, their journey through the quantum foam could be ever so slightly slower. The idea is that the foamy structure of spacetime acts like a kind of cosmic molasses for these high-energy travelers. As a photon zooms through the vacuum, it isn't traversing a perfectly smooth continuum. It's navigating a turbulent sea of fluctuating geometry, a landscape of minuscule quantum gravitational bumps and wrinkles, while a low-energy photon might simply glide over this microscopic roughness. A much more energetic photon with a smaller wavelength would be more sensitive to the fine-grained texture. It would, in a sense, feel the foam more directly, interacting with the tiny spacetime defects in a way that very slightly impedes its progress. The higher the photon's energy, the more pronounced this slowing effect should be. This isn't a dramatic effect you could ever notice with the naked eye. the predicted time delays are unimaginably small, perhaps amounting to a few milliseconds over a journey of billions of years. But for physicists, that tiny delay would be a revolutionary discovery, a direct whisper from the Planck scale. To catch this whisper, scientists have turned their instruments to the most powerful and distant flashbulbs in the universe, gamma-ray bursts. These are cataclysmic events, often the death throes of massive stars or the collisions of neutron stars, that release in a few seconds more energy than our Sun will emit in its entire 10 billion-year lifetime. Crucially, they flood the cosmos with a torrent of photons across a huge range of energies, from low-energy radio waves to immensely high-energy gamma rays. According to the foam-induced speed variation theory, the different photons from a single gamma-ray burst should not all arrive at Earth at exactly the same moment. The highest energy gamma rays, those interacting most strongly with the spacetime foam, should lag a tiny bit behind their lower energy cousins from the same event. It's like firing a shotgun blast of different-sized pellets through a dense fog. The smallest, lightest pellets might be slowed down more by the fine mist, arriving at the target just after the larger, heavier shot. By meticulously analyzing the arrival times of these different photons after their multi-billion-year voyage, we can, in principle, detect the subtle drag of the quantum foam. Several ambitious experiments have been designed to hunt for this effect. Telescopes like the Fermi Gamma Ray Space Telescope and ground-based observatories like MAGIC and HESS are constantly monitoring the sky for these cosmic fireworks. When a gamma-ray burst is detected, they record the precise arrival time of every single photon across the energy spectrum with nanosecond accuracy. The data is then scoured for any correlation between a photon's energy and its travel time. A positive result, a consistent tiny delay for the highest energy photons, would be monumental. It would provide the first ever experimental evidence for a quantum structure of spacetime. It would be a direct probe of quantum gravity, a field of physics that has until now been almost purely theoretical. The implications would ripple through every corner of physics, forcing us to rewrite our understanding of the fundamental fabric of the cosmos and potentially validating one of the key predictions of theories like loop quantum gravity. However, the story is not so straightforward. The hunt for these speed variations has proven to be incredibly difficult, and so far the results have been frustratingly ambiguous. Some analyses of specific gamma-ray bursts have shown tantalizing hints of the expected time delays, sending waves of excitement through the astrophysics community. But other studies, sometimes of different bursts or using different statistical methods, have found no delay at all, suggesting that light speed remains perfectly constant regardless of energy. This inconsistency itself is a crucial piece of the puzzle. It could mean that the foam's effect is subtler than our current models predict, or that it only manifests under certain conditions we don't yet understand. It's also possible that other astrophysical processes occurring within the gamma-ray burst itself or during the light's long journey could be mimicking or masking the quantum gravitational signal. Untangling the true signature of spacetime foam from the complex astrophysical background noise remains one of the great experimental challenges of our time, a high-stakes detective story unfolding in the data streams of our most powerful telescopes. But the quantum foam's influence isn't limited to the vast, empty expanses between galaxies. Its fingerprints are also found on the most extreme objects in the universe, black holes. This brings us to a profound connection that ties the frantic activity of the microscopic world directly to the thermodynamics of these cosmic giants. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking made a revolutionary discovery. Black holes are not the simple, featureless voids described by classical general relativity. They possess entropy, a measure of disorder or hidden information. The Bekenstein-Hawking formula tells us that the entropy of a black hole is astronomical, and it's proportional to the area of its event horizon, the point of no return. This was a stunning revelation because in thermodynamics, entropy is typically related to volume. For a black hole, all its hidden information, all the complexity of the stars, gas, and planets it has consumed, seems to be encoded not within its volume, but on its two-dimensional surface. This was the first strong hint of the holographic principle we discussed earlier. So, where is all this information stored? What are the microscopic atoms that account for a black hole's unimaginable entropy? This is where the quantum foam makes its grand entrance. The leading theory suggests that the immense entropy of a black hole is stored in the microscopic, fluctuating configurations of the quantum foam that constitutes its event horizon. Think of the horizon not as a perfectly smooth mathematical boundary, but as a seething, turbulent membrane of spacetime foam. At the Planck scale, this surface is a frenetic dance of virtual particles, microscopic wormholes, and fluctuating geometries. Each possible arrangement of this foam, the specific way a virtual particle pair appears, the momentary formation of a tiny wormhole, the exact fluctuation in the spacetime metric represents a distinct microstate. The entropy, then, is a count of all the possible ways the quantum foam on the horizon can be arranged while still looking from the outside, like the same black hole with the same mass, charge, and spin. To grasp this, picture the event horizon as a digital screen, but one with pixels so fine they operate at the Planck scale. The Bekenstein-Hawking entropy calculation implies that each of these fundamental pixels of area on the horizon can hold exactly one bit of information. It's as if the universe has a fundamental resolution, and the surface of a black hole is tiled with these tiny units. The quantum foam is the dynamic, physical manifestation of these pixels. Each flicker of a virtual particle, each twist in the fabric, is a pixel switching its state from a 0 to a 1 and back again. The foam's constant churn is the screen refreshing itself at an unimaginable rate, with the sum total of all these possible configurations amounting to the black hole's enormous entropy. This provides a breathtakingly concrete physical picture for what was once a purely abstract formula. The information about everything that has fallen into the black hole isn't lost inside the singularity. It is smeared and stored across this foamy, holographic surface, with each bit of data tied to a tiny portion of the horizon's area. This idea successfully bridges the worlds of gravity, quantum mechanics, and information theory, suggesting that at the most fundamental level, the universe is about information, and the quantum foam is the medium on which that information is written. Yet another theory takes the bizarre implications of the quantum foam and pushes them into even stranger territory, suggesting that this foamy medium might be the very substrate for one of the most radical interpretations of quantum mechanics ever proposed, the transactional interpretation. To understand this, we first need to recall the central mystery of the quantum world, the behavior of particles like electrons and photons that seem to exist as probability waves until the moment they are measured, at which point they suddenly and mysteriously choose a single, definite state. The standard view offers no mechanism for this. It simply gives us a mathematical recipe for calculating probabilities. The transactional interpretation, however, provides a stunningly concrete, albeit mind-bending, mechanism for this so-called collapse of the wave function, and it does so by introducing waves that travel backwards in time. In this picture, every quantum event begins when an emitter, say, an atom, sends out what is called an alpha wave. This wave propagates forward in time in the familiar way, spreading out in all possible directions as a sphere of possibility. But here is the twist: when this alpha wave encounters a potential absorber, like a detector screen or another atom, that absorber responds by emitting a confirmation wave that travels backwards in time, retracing the path of the alpha wave back to the original emitter. It is only when the original emitter and the absorber have established this handshake, this two-way transaction through waves going forwards and backwards in time, that a real, tangible particle is actually exchanged. The probability of any particular event occurring is determined by the strength of this completed transaction. So, what does this have to do with the quantum foam? The theory proposes that the foam is the physical medium that makes these bizarre time-symmetric transactions possible. The chaotic, flickering structure of spacetime at the Planck scale provides the perfect, if not the only, environment where offer and confirmation waves can seamlessly travel outside of our normal, linear flow of time. The foam's inherent probabilistic nature, its constant churn of virtual particles and fluctuating geometry, is not just background noise, it is the active, dynamic network through which these waves negotiate the terms of reality. In this view, every single virtual particle pair we've discussed, blinking in and out of existence, is not a random fluctuation but could be the signature of a tiny, transient transaction. An offer wave from the vacuum meeting a confirmation wave from the future, creating a fleeting particle-antiparticle pair before the transaction is complete and they vanish. The foam, then, is a seething cauldron of potential transactions across time, a cosmic marketplace where the past and the future are constantly in communication, bartering to define the present moment. This provides a profoundly causal, albeit deeply non-local, picture of reality. It removes the seeming randomness of quantum mechanics and replaces it with a deterministic process, but one where causes can come from the future just as easily as from the past. The spooky action at a distance of quantum entanglement finds a natural explanation here. Two entangled particles remain linked because their original transaction at the moment of their creation involved confirmations waves that locked their fates together across space and time. It elegantly explains the famous double-slit experiment, where a single particle seems to pass through two slits at once. In the transactional view, the emitter sends out an offer wave that goes through both slits. Absorbers at various points on the detector screen in the future send confirmation waves back through time. The transaction that finally completes, and thus determines where the particle is detected, is the one where the forward-moving offer wave and the backward-moving confirmation wave constructively interfere most strongly, creating the familiar interference pattern. The particle never had to choose a path. The entire history of the event, from emission to absorption, was negotiated in a single, timeless transaction facilitated by the quantum foam. This interpretation forces us to confront our most basic assumptions about time and causality. Our everyday experience tells us that time flows inexorably forward, that the past is fixed and the future is undetermined. The transactional interpretation, rooted in the physics of the foam, suggests this is an illusion. The universe at its most fundamental level may be a static, four-dimensional block where the past, present, and future all exist equally, and what we perceive as the flow of time is merely our conscious journey through this block, witnessing the completion of these countless pre-negotiated transactions. While this theory remains highly speculative and is far from the mainstream, it showcases the incredible power of the quantum foam concept. It's not just a placeholder for our ignorance, it's a fertile ground for the most profound and radical reimaginings of reality, suggesting that the answers to the universe's biggest questions may lie in understanding how this turbulent, foamy foundation allows for a dialogue not just across space but across time itself. If the fabric of reality were a superfluid, what strange and beautiful properties would it possess? This is the core of a theory that proposes spacetime itself is not just a stage but a fluid, a perfect, frictionless quantum superfluid. In this radical reimagining, the universe we inhabit is akin to a cosmic ocean of this extraordinary substance, and the quantum foam we've been exploring is not a sign of chaos, but the vibrant, dynamic texture of this fluid in motion. Think of the most perfect fluid imaginable, one with absolutely zero viscosity, where flow is perpetual and resistance is non-existent. Now, imagine that this fluid is the very substrate of space and time. According to this model, the vacuum is not empty. It is filled with this superfluid medium, and what we perceive as particles and forces are merely excitations and patterns within it. The constant, frantic bubbling of the quantum foam, then, can be seen as the natural roiling of this superfluid at the tiniest of scales, a sea of quantum turbulence where tiny whirlpools and ripples are constantly forming and dissolving. These are the vortices and phonons, the fundamental vibrations and topological defects in the superfluid spacetime. A virtual particle pair blinking into existence could be a microscopic vortex-antivortex pair, a tiny tornado of spinning spacetime that momentarily twists off from the background before annihilating itself. The foam's probabilistic nature directly reflects the quantum mechanical behavior of this underlying superfluid medium. The most profound implication of this superfluid spacetime theory is its potential to explain gravity not as a fundamental force, but as an emergent phenomenon, much like the waves and currents we see in a river. In our everyday world, the flow of water is governed by the laws of fluid dynamics laws that emerge from the collective interactions of countless water molecules. The molecules themselves don't know anything about pressure gradients or vortex shedding. Those are large-scale, emergent properties. In exactly the same way, this theory suggests that Einstein's general relativity and its description of gravity as the curvature of spacetime is not the final, fundamental story. Instead, gravity could be an emergent, hydrodynamic effect of the deeper superfluid dynamics. The presence of a massive object like a star would be analogous to a spinning ball creating a whirlpool in the superfluid. The way the fluid flows around the ball, creating a depression that draws other objects inward, is a perfect analogy for how mass tells spacetime how to curve, and how curved spacetime tells mass how to move. In this view, a black hole's event horizon might be akin to a gravitational bathtub drain, a vortex in the superfluid spacetime from which nothing can escape. The incredible smoothness and lack of friction in the superfluid would explain why objects in free fall experience weightlessness. They are simply moving with the natural, undisturbed flow of the spacetime fluid. This elegant framework also offers a potential resolution to the problem of singularities. In classical fluid dynamics, if you try to model a vortex down to an infinitely small point, your equations break down and predict infinite velocities and densities. But we know that in a real fluid like water, a vortex has a finite structure. It has a core. In the same way, a superfluid spacetime would have a natural cutoff scale, likely the Planck length, preventing the formation of true mathematical singularities. The core of a black hole would not be a point of infinite density, but a region of extremely high yet finite turbulence in the superfluid. This naturally avoids the infinities that plague classical general relativity and provides a more complete physical picture of these cosmic monsters. The theory even suggests a stunning connection to the famous holographic principle. The way information about a volume of a fluid can sometimes be encoded on its boundary is a known concept in fluid dynamics. In a similar, though far more abstract, way, the information about the interior of a black hole could be encoded on its event horizon, which would act as the boundary surface of the superfluid vortex. This superfluid model of spacetime is a powerful, unifying vision. It takes the frenetic activity of the quantum foam and gives it a coherent physical identity, transforming it from a sign of random chaos into the essential, dynamic character of a fluid-like reality from which everything we know, matter, energy, space, time, and even gravity ultimately emerges. This turbulent, ever-shifting foundation of reality, the quantum foam, might hold the key to one of the most persistent mysteries in all of science: why the bizarre, probabilistic world of the quantum doesn't manifest in our everyday classical reality. This is the problem of quantum decoherence, and the foam offers a compelling and elegant solution. To understand this, we need to revisit the central weirdness of quantum mechanics. In the quantum realm, particles don't exist in a single, definite state. An electron isn't simply here or there. It exists in a blurry cloud of probability, a superposition of all its possible locations and states simultaneously. It's only when we observe or measure the particle that this probability wave, as it's called, seems to collapse into a single, definite outcome. This abrupt transition from the fuzzy quantum world to the sharp classical world is known as the measurement problem, and for a century it has baffled and divided physicists. What constitutes a measurement? Why does the act of observation force the quantum system to make up its mind? The theory of quantum decoherence, with the quantum foam as its prime suspect, provides a mechanism for this transition without needing a conscious observer or any mystical collapse. The idea is that a quantum system, no matter how well isolated, is never truly alone. It is constantly, relentlessly interacting with its environment. And the most fundamental, inescapable environment of all is the quantum foam, the seething sea of virtual particles and fluctuating space-time geometry that underlies everything. Imagine you have a perfectly balanced single electron in a delicate superposition, existing in two places at once. Now envision this electron not in a perfect vacuum, but submerged in the churning ocean of the foam. Every fraction of a second, countless virtual particles are popping into existence all around it. Some of these virtual photons will briefly interact with the electron, subtly bouncing off it and then vanishing. Crucially, these interactions are ever so slightly different depending on which part of the electron's probability cloud the virtual particle encounters. A virtual photon interacting with the left version of the electron will gain a tiny bit of phase information different from a photon interacting with the right version. Think of it like this: you're trying to have a hushed, private conversation with a friend in the middle of a crowded, noisy party. The intricate details of your conversation, the quantum coherence, are fragile. The constant barrage of background noise, the snippets of other people's chatter, and the general hubbub of the room make it impossible to maintain that delicate, private information. The noise from the environment constantly intrudes, scrambling your message and forcing it to blend in with the macroscopic certainty of the party's overall din. In this analogy, your private conversation is the quantum superposition, and the loud party is the environment of the quantum foam. The incessant bombardment by virtual particles acts as a form of constant, involuntary measurement. Each tiny interaction steals a little bit of the quantum system's phase information, the precise relationship between the different possibilities in its superposition, and carries it away into the vast, uncontrollable environment. This process is decoherence. It doesn't destroy the quantum nature of the particle. Rather, it entangles the particle's state with the state of the environment. The information about the superposition isn't lost. It's simply scattered and delocalized across countless virtual particles in the foam, becoming effectively irretrievable. For all practical purposes, this is indistinguishable from a collapse. Once the phase information is lost to the environment, the quantum system can no longer exhibit telltale signs of superposition like interference patterns. It begins to behave like a classical object with definite properties. The reason why large objects, cats, baseballs, planets, don't exist in superpositions is because they are composed of trillions upon trillions of particles, each one constantly being jostled and measured by the quantum foam. Their decoherence time is unimaginably short, effectively instantaneous. A single electron might maintain its coherence for a comparatively long time in a highly shielded lab, but a macroscopic object is so thoroughly and continuously coupled to the foamy environment that its quantum weirdness is erased before it can ever manifest. In this view, the quantum foam isn't just a passive backdrop. It is an active participant in shaping reality, acting as a universal decohering engine that continuously resolves quantum potentialities into the definite classical world we experience. It provides a physical, continuous process that explains the emergence of the classical from the quantum, solving the measurement problem by showing that measurement is happening everywhere all the time, at the most fundamental level of spacetime itself. Stephen Hawking, in his quest to understand the ultimate origin of everything, proposed a theory so elegant and radical that it redefines the very meaning of beginning. This is the no-boundary proposal, and to grasp its full power, we need to venture into the strange domain of imaginary time. We're all familiar with regular, real time, the one-way street from past to future that we experience every day. But in theoretical physics, we can use a mathematical trick, replacing real time with an imaginary time dimension that behaves more like a direction in space. This isn't time travel in the science fiction sense. It's a powerful tool that transforms the problem of the universe's birth. In the framework of imaginary time, the frenetic, chaotic quantum foam we've been discussing undergoes a profound metamorphosis. Its sharp, probabilistic spikes and the terrifying singularity of the Big Bang smooth out into a gentle, curved, and finite geometry. This new shape has no boundary, no edge, no starting point that demands a before. The most famous analogy for this is the Earth's surface. If you start walking in any direction on our planet, you never encounter a sharp edge or a sign saying "Stop, creation point ahead." The surface is finite in area, yet it has no boundary. Hawking's proposal suggests the entire universe in imaginary time has a similar four-dimensional geometry. It's a closed surface without an edge, meaning the question, what happened before the Big Bang, becomes as meaningless as asking, what is north of the North Pole? In this no-boundary picture, the universe's origin story shifts dramatically. There is no primordial explosion from a point of infinite density, no mysterious primal cause that set everything in motion. Instead, the universe spontaneously and smoothly comes into existence through a quantum process. Think of it like the formation of a bubble in a boiling liquid. There isn't a specific moment you can pinpoint when the bubble began. It simply condenses out of the background activity, a seamless transition from not quite there to fully formed. In the same way, our entire cosmos is envisioned as condensing out of the quantum foam, but in imaginary time, this foam isn't a turbulent sea. It's a calm, probabilistic landscape where the most likely history for the universe is one that smoothly curves from nothing into a tiny, nascent cosmos and then expands into the vast reality we see today. This spontaneous creation isn't a violation of physical laws because the positive energy of all the matter and radiation in the universe is perfectly balanced by the negative gravitational energy of its own spacetime curvature. The total energy of the cosmos in this view is zero. It's the ultimate free lunch, a universe created from nothing because nothing in this context has a precise physical meaning, a state of zero total energy. So, what role does our familiar, chaotic quantum foam play in this serene, self-creating universe? The foam is the fundamental substrate from which this smooth, no-boundary geometry emerges. The frantic bubbling of virtual particles and fluctuating geometry in real time can be seen as different, probabilistic pathways in the sum over histories. Most of these pathways are wild and complex, but the no-boundary proposal identifies the most probable, dominant history, the one where the foam's structure, when viewed through the lens of imaginary time, averages out to form that perfectly smooth, finite, and unbounded surface. It's akin to the way the jittering of individual water molecules averages out to create the calm, smooth surface of a pond. The quantum foam doesn't disappear, it is the raw material, and the no-boundary condition is the mold that shapes it into a coherent, self-consistent whole. This provides a stunningly elegant answer to the problem of the initial singularity, completely avoiding the breakdown of physics that a true beginning point implies. The universe simply is, in the same way the surface of the Earth simply is. It doesn't need an external creator or a first cause. Its existence is a natural consequence of the laws of quantum gravity and the unique boundary-less geometry they favor. This proposal represents one of the most profound and philosophically satisfying visions of our cosmic origins, suggesting that the universe, in its most fundamental form, is a self-contained, self-actualizing entity born from the seamless marriage of quantum possibility and geometric elegance. Our earlier look at the cosmological constant presented a stark puzzle, a theoretical prediction for vacuum energy that is catastrophically large, set against a measured reality that is almost zero. But what if that tiny, positive number isn't a constant at all? This brings us to a fascinating class of theories that reanimate the vacuum, proposing that the energy of the quantum foam isn't a fixed feature of the cosmos but something dynamic, something that evolves. This is the realm of quintessence, where a cosmic scalar field permeates all of space, its energy slowly changing over the eons, and its interaction with the quantum foam could be the key to understanding why our universe is so hospitable. Quintessence, named after the classical fifth element thought to fill the heavens, is not a new type of particle in the traditional sense. Instead, think of it as an invisible, cosmic energy field that exists everywhere, a bit like the Higgs field, but with a crucial difference: its energy density is not locked in. It can vary across space and, most importantly, evolve in time. In the early universe, this field might have been dormant, or its energy might have been locked away in a high-energy state. But as the cosmos expanded and cooled, the field could have begun to slowly roll down a gentle slope in its potential energy landscape, like a marble gradually descending a wide, shallow bowl. The energy associated with this slow, cosmic roll is what we could be measuring as dark energy. The brilliance of this idea is that it naturally explains why the universe's expansion is accelerating now, in this cosmic epoch. In the dense, early universe, the energy density of matter and radiation was overwhelming. The quintessence field's contribution was negligible, like a whisper in a hurricane. But as the universe thinned out over billions of years, the matter density dropped, while the quintessence field's energy density decreased much more slowly, or in some models even remained constant. Eventually, a crossover point was reached where this persistent field energy began to dominate the cosmic budget, and its repulsive gravitational effect started to push the expansion of the universe into overdrive. So, how does the ever-present quantum foam interact with this dynamic quintessence field? The foam isn't a passive backdrop here, it's an active participant. The seething sea of virtual particles and fluctuating geometry provides a medium through which the quintessence field operates. One compelling possibility is that the immense calculated energy of the quantum foam, the source of the cosmological constant problem, is real, but it is almost perfectly cancelled out by the dynamic energy of the quintessence field. Imagine the raw vacuum energy as a deafening, constant noise. The quintessence field could be acting as a form of active noise cancellation, producing a signal that is almost exactly the opposite, leaving behind only the faintest residual hum that we detect as dark energy. This cancellation wouldn't need to be inexplicably fine-tuned from the beginning. Through a process known as scanning, the quintessence field could have dynamically adjusted itself over cosmic history, its value shifting until it nearly neutralized the colossal vacuum energy, leaving the tiny, observable residue we see today. In this view, the smallness of the dark energy isn't a bizarre accident. It's the natural end result of a cosmic balancing act that has been playing out for 14 billion years. This dynamic interplay offers a way to address other cosmological puzzles as well. A simple, constant cosmological constant would mean that dark energy's push has been unchanging, leading to a specific future for the universe, a perpetual, accelerating expansion that eventually tears apart all bound structures. But a dynamic quintessence field opens up other destinies. Depending on the shape of its potential energy landscape, the field's energy could eventually dissipate, causing the acceleration to stop and potentially allowing gravity to reassert its dominance in a big crunch. Or it could strengthen, leading to an even more violent end known as the Big Rip, where the fabric of spacetime itself is torn apart. The fact that we observe an acceleration that is relatively recent in cosmic history fits nicely with a dynamic model where the quintessence field is only now coming to dominate. By tying the force driving the universe's expansion to a dynamic field interacting with the quantum foam, we replace a static, mysterious number with a rich, evolving story. A story that connects the frantic activity of the Planck scale to the ultimate fate of the entire cosmos. Now we turn to a mathematical perspective that argues the quantum foam is more than just a turbulent sea. It's a universe where the very coordinates of space and time are inherently fuzzy, governed by a strange new algebra. This is the world of non-commutative geometry, a theory suggesting that at the fundamental Planck scale, the order in which you measure things matters profoundly. In our everyday world and in the classical physics that describes it, geometry is commutative. What does that mean? Well, if you're giving someone directions to a cafe, you might say it's 3 blocks east and then 2 blocks north. If you instead went 2 blocks north first and then 3 blocks east, you'd end up in the exact same spot. The operations of moving east and north commute. Their order doesn't change the final outcome. We take this for granted, and it underpins our entire understanding of location and distance. But non-commutative geometry proposes that at the scale of the quantum foam, this common-sense rule breaks down. In this domain, measuring position in one direction and then in another does not yield the same result as performing the measurements in the reverse order. The very act of pinpointing a location in one dimension creates an inherent uncertainty in another, weaving a fundamental fuzziness directly into the fabric of spacetime. This isn't just a minor mathematical curiosity, it's a radical reformulation of what space is. In this framework, the smooth, continuous stage of classical physics is replaced by a geometric structure that is fundamentally granular and uncertain, much like the quantum foam itself. The mathematics describes a reality where spacetime points are not infinitely sharp, well-defined dots. Instead, they are replaced by fuzzy, overlapping blobs or smeared-out regions. You cannot say a particle is at an exact point with perfect precision because, according to this theory, such a point does not exist in any meaningful sense. The universe has a fundamental resolution, and trying to look closer than that is like trying to see the individual pixels on a screen by pressing your eye right up against it. You just get a blur. This provides a beautiful and direct mathematical model for the foamy texture we've been discussing. The constant churn and fluctuation isn't just something happening in spacetime, it is spacetime. The foam is the physical manifestation of this non-commutative algebra, where the uncertainty in measurement is not a limitation of our instruments, but a fundamental property of reality. To grasp this, consider a simplified analogy from the quantum world itself. You may have heard of Heisenberg's uncertainty principle, which states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more you pin down one, the more the other becomes blurred. Non-commutative geometry applies a similar logic to the very coordinates of spacetime. Imagine trying to measure the location of an event with a mythical, perfect microscope. You first try to determine its x-coordinate with ultimate precision. According to this theory, the act of making that measurement so precisely will inevitably disturb your subsequent measurement of its y-coordinate. The final position you get is not a point, but a small, fuzzy patch, a direct consequence of the fact that the x and y coordinates do not commute. This fundamental graininess means that the idea of a point-like elementary particle is an illusion. Particles aren't tiny, hard balls. They are more like probability clouds or excitations spread out over these fuzzy blobs of spacetime. This elegantly does away with the troublesome infinities that often arise in quantum field theory when particles are treated as perfect points, suggesting that the fuzziness of the foam acts as a natural regulator for the universe. The implications of this reach into the heart of quantum gravity. If spacetime is non-commutative, then the wild fluctuations of the quantum foam have a built-in structure. They are not purely random. This geometry provides a potential pathway to unify general relativity with quantum mechanics by showing how a smooth, classical spacetime can emerge from this underlying fuzzy quantum structure. Just as the smooth flow of a liquid emerges from the chaotic motion of its molecules, the four-dimensional continuum of Einstein's theory could be the large-scale average of countless non-commutative blobs interacting with one another. This perspective transforms the quantum foam from a mysterious, chaotic frenzy into a structured, though deeply strange, geometric reality. It suggests that the universe is not built from tiny billiard balls on a smooth table, but from an interwoven, fuzzy tapestry where the threads of space and time themselves are fundamentally blurred, creating the dynamic and probabilistic stage upon which all of existence plays out. Now we venture into a theory that expands our cosmic perspective to almost unimaginable proportions, connecting the seething quantum foam beneath our feet to an infinite tapestry of realities. This is the idea that our entire universe, with all its hundreds of billions of galaxies, might be nothing more than a single bubble in a vast, frothing cosmic sea, a multiverse. And the quantum foam may be the very breeding ground from which these bubble universes are born. The concept stems from the theory of eternal inflation, which suggests that the rapid expansion of space, known as inflation, didn't just happen once in our distant past and then stop. Instead, it may be an eternal, ongoing process occurring across a much grander meta-reality often called the multiverse. In this picture, what we call the Big Bang was not the absolute beginning of everything, but a local event. The moment our particular bubble of stabilized spacetime nucleated and began its own internal expansion and evolution. So, how does this connect to the quantum foam? The link is forged through a process known as bubble nucleation. Imagine the primordial state of the multiverse as an immense, high-energy quantum field, sometimes called the inflaton field. This field is in a state of constant, frantic fluctuation, a direct analog of the quantum foam but on a meta-cosmic scale. Now, within this seething, high-energy background, random quantum fluctuations can occasionally cause a tiny region of the field to tunnel through an energy barrier and drop into a lower, more stable energy state. This is analogous to a bubble of steam forming in a pot of boiling water. In the superheated water, tiny pockets of vapor spontaneously appear. Most of them collapse almost instantly, but some reach a critical size and expand rapidly. In the cosmic context, when a region of the inflaton field makes this quantum jump to a lower energy, it creates a pocket of true vacuum surrounded by the high-energy false vacuum of the multiverse. This pocket is a nascent universe, and the energy released by this phase transition fuels a tremendous, rapid expansion, the inflation that shapes our cosmos. The quantum foam of the meta-reality provides the statistical noise, the random kicks that allow these universe-forming fluctuations to occur. Our entire reality could be the result of one such fortunate quantum kick in an endless, frothing ocean of possibilities. The truly staggering implication of this theory is that this process is likely happening everywhere all the time. The eternal inflationary background is continually giving birth to new bubble universes, each one pinning off from the multiverse like soap bubbles separating from a wand. This creates a truly infinite multiverse, a cosmic foam where bubbles collide, merge, and drift apart, each one a self-contained cosmos with its own Big Bang and its own subsequent history. And here is where the theory becomes even more profound. When a bubble universe nucleates, the specific way the inflaton field settles into its low-energy state can determine the fundamental physical constants and laws within that bubble. The strength of gravity, the mass of an electron, the number of spatial dimensions, all of these could be randomly set during the nucleation process. In this view, we find ourselves in a universe with constants perfectly tuned for the formation of stars, planets, and life, not because of any grand design, but simply because an inconceivable number of universes were generated, each with different laws. In the vast majority, the constants were wrong, and those universes remained sterile and empty, unable to generate complexity. We, of course, can only exist in one of the rare, bio-friendly bubbles. This offers a powerful, if humbling, explanation for the apparent fine-tuning of our cosmos, reframing it as a form of cosmic natural selection on a multiversal scale. The connection to the quantum foam we've explored throughout this journey is therefore twofold. Firstly, the multiverse itself can be seen as a macroscopic manifestation of a foamy, fluctuating structure. Secondly, and perhaps more intimately, the same kind of quantum jitter that creates virtual particles in the vacuum of our universe is the very engine that creates entire universes in the greater multiverse. The microscopic foam within our space-time and the macroscopic foam of the multiverse are different scales of the same fundamental, probabilistic nature of reality. Our universe is not just resting on a quantum foam, it is a child of it, a single, stable pattern that condensed out of an eternal, turbulent genesis. This perspective suggests that creation is not a one-time event but an ongoing, endless process, with new realities constantly blinking into existence, each one a grand experiment in physics, most of them doomed to emptiness, but a rare few, like our own, blossoming into the rich complexity we are fortunate enough to observe and ponder. Building on this cosmic perspective, we now descend back to the most fundamental level, where a revolutionary theory is emerging that recasts the entire nature of the quantum foam, not as a chaotic frenzy, but as a sophisticated cosmic computer designed to protect the integrity of reality itself. This is the astounding proposal that space-time and its foamy structure act as a giant quantum error-correcting code. To grasp this, we first need to understand a monumental challenge in quantum computing. Quantum information is incredibly fragile. The delicate state of a quantum bit or qubit, which can be a 1, a 0, or a superposition of both, can be easily corrupted by the slightest interaction with its environment, a process we call decoherence. To build a functional quantum computer, we need a way to protect this information. Error-correcting codes are the solution. They work by encoding a single, fragile piece of quantum information across a complex network of many physical qubits. The key is that the true, logical information isn't stored in any one location. It is spread out or delocalized across the entire network. If a local error occurs, if one of the physical qubits gets flipped or disturbed, you can't actually tell by looking at that single qubit. The error only becomes detectable when you examine the collective, global pattern of the entire network. By measuring this pattern, you can diagnose what went wrong and apply a correction, all without ever directly measuring, and thereby destroying the fragile original information that is safely hidden within the system. Now apply this logic to the cosmos. The holographic principle, which we explored earlier, suggests that all the information describing our three-dimensional universe is stored on a two-dimensional boundary. But how is that information protected as it is projected into the volume we inhabit? This is where the quantum error-correcting code comes in. The theory posits that the quantum foam, that seething network of fluctuating geometries, virtual particles, and microscopic wormholes, is the physical implementation of this code. The foam isn't random noise, it is the intricate dynamic medium that actively encodes and protects the universe's quantum information. Each fluctuation, each virtual particle pair, each twist in the fabric is like a physical qubit in a cosmic quantum computer. The information about the location of a particle, the value of a field, or the curvature of spacetime isn't stored in one specific pixel of the foam. Instead, it is spread out holographically across a vast, non-local region of this foamy network. A local disturbance, say, a high-energy particle zipping through a region of space, might disrupt a few of these foam qubits, but because the information is redundantly stored across the entire system, that local error doesn't destroy the cosmic data. The true, logical state of the universe remains intact and uncorrupted, hidden in the global, entangled relationships within the foam. This leads to one of the most profound implications of this idea. Gravity itself may emerge as the force that corrects these errors. In this picture, what we perceive as the gravitational force is not a fundamental interaction but a thermodynamic and informational phenomenon. When matter or energy disturbs the quantum foam, when it introduces an error into the cosmic code, the system responds to correct that error and restore the integrity of the information. This corrective response manifests as an attractive force. Imagine you drop a rock into a calm pond. The rock creates a disturbance, a local deformation of the water's surface. The water responds by pushing back, creating ripples that work to smooth out the deformation and return the surface to equilibrium. In the error-correcting foam, a massive object like a planet is like that rock. Its presence is a persistent error in the space-time code. The foam's inherent dynamics work to heal this error, to push the system back towards its baseline state. This collective, restorative effort is what we feel as gravity. The planet tells the space-time code how to be disturbed, and the code's corrective action tells the planet how to move. This provides a breathtakingly elegant unification of information and geometry. The geometry of space-time, its curvature, is directly tied to the configuration of the error-correcting code. A black hole, with its immense entropy, represents a state where the local errors have become so overwhelming that the code can no longer correct them from the inside. The information becomes scrambled and is only accessible from the boundary, the event horizon. To visualize this, think of a magnificent tapestry viewed from a distance. You see a smooth, continuous image, a landscape, perhaps. This is like our classical space-time. But if you move closer, you see the image is actually woven from countless individual threads. Now, imagine this tapestry is not just a picture, but a living, self-repairing system. If you were to cut a single thread, the overall image would remain perfectly clear because the information for that part of the picture is woven across many threads. The tapestry has built-in redundancy. The quantum foam is that cosmic tapestry, and gravity is the process that automatically reweaves any broken threads to maintain the coherent picture of reality. This theory fundamentally shifts our perspective on the foam's turbulence. The constant bubbling isn't a sign of chaos, but of a system constantly checking and correcting itself, maintaining the stability of the universe against the relentless pressure of quantum uncertainty. It suggests that the order and predictability we experience in the cosmos is not a given, but an active achievement, a continuous cosmic computation running on the frothy processor of spacetime itself, ensuring that the universe doesn't simply glitch out of existence. But what if the very rules that govern the motion of light and matter are not the immutable laws we believe them to be? This brings us to a theory that strikes at the heart of Einstein's special relativity, proposing that the quantum foam doesn't just slow down light, but fundamentally rewrites the formula for how everything moves. These are modified dispersion relations, and they suggest that the seething, foamy texture of spacetime causes particles to propagate differently depending on their energy. In our standard classical understanding, this relationship is governed by Lorentz invariance, a cornerstone of modern physics that ensures the speed of light in a vacuum is constant for all observers, and that the laws of physics are the same everywhere. This principle gives us a very specific and elegant equation, the dispersion relation, that connects a particle's energy to its momentum. For a photon, which is massless, this relationship is beautifully simple. Energy is directly proportional to momentum, resulting in its constant universal speed. But if spacetime is granular and foamy at the Planck scale, this perfect symmetry might be broken. The idea is that a high-energy particle, with a wavelength small enough to feel the bumps and wrinkles of the foam, would interact with this microscopic graininess. This interaction would ever so slightly alter its trajectory and energy-momentum relationship, as if it were moving through a medium with a subtle, energy-dependent refractive index. The photon's speed would not just be slowed, the entire foundational equation describing its motion would require tiny corrective terms. These modifications are predicted to be minuscule, proportional to the particle's energy divided by the immense Planck energy. For everyday particles and light, this effect is zero for all practical purposes. But for the most energetic particles in the universe, the effect, while still incredibly small, could in principle be detected. To hunt for this fundamental breakdown of Lorentz invariance, scientists have turned to nature's most powerful particle accelerators, the violent cosmic events that produce ultra-high-energy cosmic rays. These are not rays of light, but actual subatomic particles, most often protons or atomic nuclei, that have been accelerated to energies millions of times greater than anything we can achieve in the Large Hadron Collider. They are the most energetic particles known to exist, and they travel across the universe for millions or even billions of years to reach us. According to theories with modified dispersion relations, these cosmic travelers should be the most sensitive probes of the quantum foam's structure. Their immense energy gives them incredibly small wavelengths, allowing them to interact significantly with the Planck-scale graininess of spacetime. This interaction would have two potential and dramatic observable consequences. The first concerns their longevity. In our standard model of particle physics, ultra-high-energy cosmic rays should not be able to travel very far through the cosmos. They interact with the low-energy photons of the cosmic microwave background radiation, the afterglow of the Big Bang, in a process called the Greisen-Zatsepin-Kuzmin, or GZK cutoff. A cosmic ray proton colliding with a microwave background photon should create new particles, sapping the proton's energy over a relatively short distance. This means that we should see very few cosmic rays with energies above a certain threshold, as they would have been slowed down long before reaching Earth. Astonishingly, we have detected a handful of these cosmic rays with energies far beyond this predicted cutoff. One potential explanation is that Lorentz invariance is indeed modified. If the dispersion relation for these ultra-high-energy protons is altered, the threshold energy required for them to interact with the background photons and create new particles could be shifted. They might simply not see the microwave background in the same way, allowing them to travel vast cosmological distances without losing their energy, almost as if they were ghosts slipping through a wall that should have stopped them. The second consequence involves a different kind of cosmic messenger, high-energy gamma-ray photons. If the quantum foam modifies the dispersion relation for light, then two photons of different energies emitted simultaneously from the same cosmic explosion, like a gamma-ray burst, would not necessarily arrive at Earth at the same time. We touched on this earlier with the idea of a varying speed of light, but modified dispersion relations provide a more formal, rigorous framework for this phenomenon. The time delay between a high-energy photon and a low-energy one would not be random. It would depend in a specific, calculable way on their energy difference and the distance they have traveled. By meticulously analyzing the arrival times of photons across a vast energy spectrum from these distant events, astronomers can search for this signature energy-dependent delay. A positive detection would be a direct measurement of the foamy structure of spacetime, confirming that Lorentz invariance is not a perfect symmetry of nature, but an emergent, approximate one that holds true only in the low-energy world we typically inhabit. It would reveal that the universe has a fundamental preferred frame of reference, the rest frame of the quantum foam itself. The ongoing hunt using instruments like the Pierre-Auger Observatory for cosmic rays and the Fermi Gamma-Ray Space Telescope for gamma rays sits at the frontier of experimental physics. The data so far has constrained many proposed models of Lorentz invariance violation, pushing the possible energy scale for such effects even closer to the remote Planck energy. Yet the tantalizing detection of a few super-GZK cosmic rays keeps the possibility alive, a persistent whisper that the ultimate laws of motion are written not on a smooth, continuous stage, but on a dynamic, grainy substrate that reveals its true nature only to the most energetic particles in existence. Now, as we continue to push at the boundaries of what is real, we encounter a phenomenon that forces us to confront a startling truth. Reality itself depends on your state of motion. This is the Unruh effect, a prediction of quantum field theory so strange it suggests that an astronaut undergoing constant acceleration would find themselves enveloped in a warm bath of radiation, while a stationary observer coasting through the same patch of space would swear it was completely empty and cold. The key to this bizarre discrepancy lies in the fundamental nature of the quantum vacuum. We've established that what we call empty space is a seething foam of virtual particles. For an inertial observer, one moving at a constant velocity, this foam remains just that, a background of unobservable fluctuations. But for an accelerating observer, something profound changes. Their acceleration through the vacuum effectively acts like a constant jolt to the system, a persistent kick that provides the energy needed to promote some of these virtual fluctuations into real, detectable particles. From the accelerating astronaut's perspective, they are surrounded by a thermal glow of radiation, a warm universe popping into existence just for them, with a temperature directly proportional to their acceleration. The harder they fire their engines, the hotter this ghostly bath becomes. So, how is this ethereal glow connected to the quantum foam we've been exploring? The theory posits that the Unruh radiation is not some separate phenomenon, but a direct and dramatic manifestation of the foam itself. The acceleration doesn't create particles out of nothing. It simply stirs the ever-present foam with enough vigor to make its hidden activity visible. Think of the quantum foam as a perfectly still, dark pond whose surface is invisibly textured with countless tiny ripples. An observer floating gently on the pond sees nothing but calm. But an observer violently thrashing through the water would see a spray of droplets flying everywhere, making the unseen texture of the water's surface dramatically apparent. In the same way, an accelerating observer's motion through spacetime thrashes the quantum foam, kicking the virtual particle-antiparticle pairs with enough energy to prevent them from annihilating each other back into the vacuum. The transient wormholes and geometry fluctuations of the foam are agitated into a detectable state. This provides a breathtaking physical picture. The particles detected in the Unruh effect are not independent entities, but excited states of the spacetime foam itself. The warm bath of radiation is the literal heat of excited spacetime. This leads to one of the most profound implications of this theory. It blurs, perhaps even erases, the line between particles and geometry. In our everyday classical view, a particle is a thing and spacetime is the stage upon which it moves. They are fundamentally different categories of existence. But the Unruh effect, interpreted through the lens of the quantum foam, suggests this is an illusion. What an inertial observer calls empty spacetime and what an accelerating observer calls a cloud of particles are two different descriptions of the exact same underlying reality, the dynamic, frothing structure of the quantum foam. A particle, in this view, is not a foreign object placed in spacetime. It is a particular, stable excitation of spacetime. The geometry of the universe is not passive. It is an active, vibrating medium, and particles are its resonant notes. This perspective offers a stunning unification. It suggests that the fundamental building blocks of matter are not separate from the fabric of the cosmos, but are, in fact, intricate patterns woven directly from that fabric. The distinction between the actor and the stage dissolves, revealing a universe where everything, every electron, every photon, every force, is a manifestation of the complex, dynamic geometry of spacetime at its most fundamental, foamy level. Yet another profound mystery arises not from the cosmos at large, but from the seemingly arbitrary numbers that define the very forces holding our world together. This is the hierarchy problem in particle physics, and it asks a deceptively simple question. Why is gravity so unbelievably weak, we're not talking about a small difference here. The strength of the electromagnetic force is about a 1 followed by 36 zeros times stronger than gravity. To grasp this, consider that a small fridge magnet can effortlessly overpower the gravitational pull of the entire Earth, lifting a paperclip against that immense weight. This staggering difference in strength is quantified as the gap between two fundamental energy scales: the electroweak scale, which is about 246 gigaelectronvolts and governs the forces that hold atoms together, and the Planck scale, which is a quadrillion times higher at 10 to the 19th power gigaelectronvolts, the energy level where gravity is expected to become. Strong as the other forces, this enormous desert between the two scales feels unnatural. In our current theories, the mass of the Higgs boson, the particle that gives mass to others, is tied to the electroweak scale. But quantum corrections from the frantic virtual particles in the foam should drive the Higgs mass, and therefore the electroweak scale, all the way up to the colossal Planck scale. For our universe to exist as it does, with atoms and molecules stable, an inexplicable and perfect cancellation of these quantum effects must occur, requiring a level of fine-tuning that seems absurd to most physicists. It's as if you balanced a pencil on its tip for 14 billion years, possible in theory, but screaming for a deeper explanation. This is where the quantum foam, and the way we conceive of its structure, offers a truly revolutionary way out. One of the most compelling solutions suggests that gravity only appears feeble because it is not confined to our familiar 3 dimensions of space. In the brain world scenario, our entire universe, all the particles and forces except for gravity, is trapped on a 3-dimensional membrane, a brane for short, floating within a higher dimensional space. Think of our reality as a magnificent 3-dimensional painting on a vast, flimsy canvas. The pigments and brushstrokes, the quarks, electrons, and photons are stuck on the canvas. They can move around its surface, but they cannot leap off. Gravity, however, is different. It is the vibration of the canvas itself, the geometry of spacetime, and in this model, it is free to propagate into the full volume of the higher dimensional space, or the bulk. This simple change in perspective has a dramatic consequence. The strength of a force is diluted as it spreads out into more dimensions. Imagine the sound from a single, tiny speaker in the middle of an empty field. If the sound waves are confined to the 2-dimensional surface of the field, their intensity diminishes fairly slowly as they travel. But if that same speaker were suspended in a vast, 3-dimensional volume of air, the sound energy would spread out in all directions, becoming incredibly faint much more rapidly. Gravity is like that speaker in the higher dimensional space. Its fundamental strength at the Planck scale might not be weak at all, but because it spreads out into these extra dimensions, its apparent strength in our 3-dimensional brain becomes diluted to the incredibly feeble level we measure. The quantum foam is the microscopic texture of this entire higher dimensional reality. The frantic bubbling and virtual particle creation we've discussed isn't just happening on our brain, it pervades the bulk. The structure of this higher dimensional foam is what determines how gravity leaks away from us. In this picture, the hierarchy problem is solved not by improbable fine-tuning but by geometry. The vast gap between the electroweak scale and the apparent Planck scale is an illusion created by the extra dimensions. The true, fundamental Planck scale where gravity becomes strong could be much, much lower, potentially even down at the electroweak scale itself. This would mean that the quantum foam's most dramatic effects, the wormholes, the spacetime discreteness, the full fury of quantum gravity, are not unreachable at 10 to the 19th power gigaelectronvolts, but could be just around the corner, awaiting discovery at energies we might one day probe with our particle colliders. The reason we don't see these extra dimensions is that they are incredibly small, curled up on themselves at a scale far tinier than an atom. Only gravity, by its very nature as the geometry of spacetime, can sense these compactified directions and leak into them. This elegant idea provides a concrete, testable prediction. If there are large extra dimensions, then at very small distances, or equivalently, at very high energies, gravity should stop behaving according to the familiar inverse square law and instead fall away much more quickly. The search for this deviation is one of the most active pursuits in experimental physics, using exquisitely sensitive tabletop experiments to measure the gravitational force between objects at microscopic distances. Finding such a breach in Newton's law would not only solve the hierarchy problem, but would provide the first direct evidence that the quantum foam has a richer, more expansive architecture than we ever dreamed, woven from more than the three spatial dimensions we call home. After exploring the universe as a superfluid and a quantum error-correcting code, we arrive at what is perhaps the most profound reimagining of reality yet, a theory that suggests the stage itself is an illusion. This is the concept of progeometry, the radical proposal that spacetime and the quantum foam dancing upon it are not the fundamental layers of reality. They are not the foundation, but rather a magnificent, emergent spectacle that arises from something even more basic, something that exists beyond the very concepts of space and time as we know them. Imagine you're watching a movie on a screen. The world you see has depth, movement, and a flowing narrative. But if you could look behind the screen, you would find that this rich, three-dimensional reality is generated by a stream of ones and zeros, a sequence of pure information. Progeometry argues that our universe operates on a similar principle. The ceaseless churn of the quantum foam, the dance of particles, and the vast expanse of the cosmos are all a grand production, emerging from a deeper, non-spatiotemporal reality built from elementary relationships or quantum bits of information. This perspective is often encapsulated in the powerful phrase, "it from bit," coined by the visionary physicist John Archibald Wheeler. He proposed that every particle, every field of force, even the fabric of spacetime itself, derives its existence, its very itness, from the answers to yes or no questions posed by the universe, from binary bits of information. In this view, the quantum foam is not a seething sea of energy in a pre-existing space. It is the visible, dynamic expression of an unimaginably complex computation. Each virtual particle pair blinking in and out of existence is not a fluctuation in spacetime, but a fluctuation of the underlying informational network. The foam's probabilistic and turbulent nature directly reflects the fundamental quantum randomness and parallel processing of this cosmic computer. The geometry of the universe, its curvature, its dimensions, its very topology, is not a given. It is a derivative property that crystallizes from the pattern of correlations and entanglement between these fundamental bits. What we perceive as a continuous, smooth fabric is at its root a tapestry woven from discrete, logical connections. To grasp this, consider the world of a massively multiplayer online game. The players experience a vast, continuous landscape with mountains, rivers, and cities. They can move through this world, interact with objects, and feel as if they are in a real place. Yet, this entire reality is generated by a server running complex code. The space of the game doesn't exist in the computer's memory in the same way it does for the players. It is an emergent property of the data structures and the relationships between them. The game's physics, gravity, momentum, collision are not fundamental laws but algorithms executed by the processor. In the progeometric universe, the quantum foam is like the dynamic, rendered graphics of this cosmic game. The underlying reality is the source code, a network of quantum bits whose interactions and logical operations give rise to the illusion of a spatial continuum and the flow of time. The foam's constant activity is the visual representation of the processor's clock cycles, updating the state of the universe moment by moment. This framework offers a breathtakingly elegant way to unify the physical world. In progeometry, the long-sought theory of quantum gravity is not about quantizing spacetime itself, because spacetime is no longer the fundamental player. Instead, gravity, along with all the other forces and particles, emerges from the collective dynamics of the underlying informational network. The force of gravity, as described by Einstein's general relativity, would be an entropic force or a consequence of the way information is scattered and hidden within the network, much like the restorative force we discussed in the error-correcting code theory. A black hole's event horizon, with its immense entropy, represents a region where the underlying informational architecture has reached a state of maximum complexity and entanglement. The Big Bang, in this view, would not be an explosion in space, but the initial boot-up sequence of the cosmic computer, the moment when the first fundamental bits became correlated and began generating the emergent phenomena of space, time, and matter. This transforms our quest for a fundamental theory from a search for the ultimate stuff of the universe to a search for the ultimate algorithm, the simple yet powerful set of rules from which all of reality computationally unfolds. This concept brings us to one of the most pivotal theories in all of modern cosmology, connecting the invisible, frothy chaos of the quantum world directly to the majestic, large-scale architecture of the universe. This is the idea that the quantum foam provided the very seeds for creation, the initial imperfections that allowed everything we see, from the smallest dwarf galaxy to the largest supercluster, to eventually form. To understand how this works, we need to rewind the cosmic clock back to the earliest moments of the universe, to a period known as cosmic inflation. Imagine the newborn cosmos, a fantastically hot, dense, and unimaginably small speck. According to the theory of inflation, this speck underwent a breathtakingly rapid exponential expansion, doubling in size over and over again in a fraction of a second. This process smoothed the universe out to an incredible degree, ironing out any major wrinkles and leaving it remarkably flat and uniform. But if it was so perfectly smooth, how did any structure ever arise? How did we get from that featureless primordial soup to a universe filled with galaxies? The answer lies in the one thing that inflation could not erase, the inherent probabilistic jitter of the quantum foam. Even during this ultra-fast expansion, the vacuum of space was not truly empty. It was filled with the inflaton field, the driving engine of inflation, and this field was subject to the same quantum rules as everything else. At the tiniest of scales, at the level of the Planck length, the inflaton field was constantly fluctuating due to the seething quantum foam beneath it. Virtual particle-antiparticle pairs related to this field were blinking in and out of existence, creating minuscule, random variations in the field's energy from one infinitesimal point to the next. These were not fluctuations in space, but fluctuations of space and the field that filled it. Under normal circumstances, these quantum jitters are completely unobservable, far too small to have any meaningful effect. But inflation acted like a cosmic magnifying glass of unimaginable power. As spacetime itself expanded at a rate faster than light, it stretched these microscopic quantum fluctuations in the inflaton field along with it. A tiny ripple in the field that was once smaller than a subatomic particle was, in less than an eye blink, stretched to a size spanning light years across. The quantum noise was imprinted directly onto the fabric of the cosmos, transformed from microscopic probabilistic fuzz into macroscopic, classical differences in the density of matter and energy. Think of it like baking a cosmic raisin bread. Before inflation, the dough representing the universe is being vigorously kneaded. The quantum foam is like the inherent tiny pockets of air and unevenness in the dough at the molecular level. You can't see them with your naked eye. Now you put the dough in a fantastically powerful oven for inflation, and it rises at an unbelievable rate. As it expands, those once invisible, microscopic air pockets are stretched into vast, macroscopic bubbles and voids within the loaf. The raisins, which represent clusters of matter, will naturally be drawn by gravity to collect in the denser regions between these bubbles. In our universe, the incredibly slight over-densities created by the stretched quantum fluctuations acted as gravitational seeds. After inflation ended, the universe was filled with a hot plasma of matter and radiation, but it was no longer perfectly smooth. It had a specific pattern of slightly denser regions and slightly less dense regions, a blueprint imposed upon it by the magnified quantum foam. Gravity then got to work on this blueprint. Over hundreds of millions of years, the slightly denser patches had slightly stronger gravity, pulling in more and more matter from their surroundings. This gravitational collapse amplified the initial tiny differences, eventually snowballing into the first stars, the first galaxies, and the vast web-like filaments of galaxy clusters we observe today. The entire cosmic web is a fossilized imprint of the quantum foam from the universe's first fleeting moments. The evidence supporting this breathtaking theory is both compelling and beautiful. It is written across the entire sky in the form of the cosmic microwave background radiation, the ancient afterglow of the Big Bang. When we map this radiation with satellites like Planck and WMAP, we are essentially taking a baby picture of the universe, a snapshot from a time when it was just 380,000 years old. This picture is not perfectly smooth. It is covered in tiny temperature variations, anisotropies, where some patches are a few millionths of a degree warmer or cooler than others. These temperature differences directly correspond to the density fluctuations imprinted by the stretched quantum foam. A slightly warmer spot was a slightly denser region of the early universe, a gravitational seed that would one day grow into a galaxy cluster. The statistical pattern of these hot and cold spots, their distribution and size, matches the predictions of the quantum fluctuation theory with stunning precision. The specific signature of these fluctuations tells us that they originated as quantum gravitational noise, the kind of noise we would expect from a frothy, probabilistic spacetime. This means that the specific arrangement of galaxies in the sky today, the location of our own Milky Way, and even the spot where you are sitting right now, can all trace their ultimate origin back to a random quantum fluctuation in the primordial foam that was amplified to cosmic proportions during that brief, violent period of inflation. The largest structures in the universe were born from the smallest possible vibrations of reality, a direct and elegant link between the quantum and the cosmic that stands as one of the most successful and profound ideas in all of science. Yet another profound challenge emerges not from the vastness of space, but from the nature of time itself. When we attempt to merge Einstein's general relativity with quantum mechanics, we are confronted with a philosophical puzzle so deep it threatens to dismantle our most basic intuition, the idea that time flows at all. In Einstein's theory, time is not a universal backdrop. It is a flexible dimension woven together with space into a single, four-dimensional block universe. The entire history of the cosmos, from the Big Bang to the distant future, simply is, with past, present, and future all existing simultaneously in this static tapestry. Yet in quantum mechanics, time plays a very different role. It is an external, absolute parameter against which the probabilistic dance of particles unfolds. The equations of quantum theory depend on a fixed, flowing time to describe how a system evolves. When we try to force these two incompatible views together into a theory of quantum gravity, which describes the foam, time itself seems to vanish from the fundamental equations. In approaches like the Wheeler-DeWitt equation, a cornerstone of quantum cosmology, the variable for time simply drops out. The result is a description of the universe that is utterly timeless at its most fundamental level. This presents us with a startling conclusion. The universe, according to our best attempts at a fundamental theory, does not evolve in time, it just is. So where does our powerful, undeniable experience of a flowing present, a fixed past, and an open future come from? This is where the quantum foam offers a potential escape route from this philosophical labyrinth. If time is not a fundamental ingredient, then it must be an emergent property, a large-scale illusion that arises from the complex relationships and interactions within the underlying foamy network. Think of it like the temperature of a gas. A single molecule doesn't have a temperature. Temperature is a collective, statistical property that emerges from the frenetic motion of trillions of molecules. In the same way, the flow of time may not be a feature of the fundamental atoms of spacetime, but a collective property that emerges from the way these atoms are correlated with one another. In the loop quantum gravity picture, the spin network that constitutes space is not static. It evolves with its connections updating and changing. But this evolution is not happening in time. The entire four-dimensional history of the network's changes is reality. Our perception of a moment called now could be our conscious awareness moving through this frozen block, like a spotlight scanning across the frames of a finished movie reel. This leads to the radical idea that time is born from change and correlation. We don't perceive time directly, we perceive that things around us are changing. The hands of a clock move, a planet orbits its star, and particles interact. What we call time is really just our way of tracking and comparing these different rates of change against each other. In the timeless quantum foam, there is no external clock, but within the foamy network, one set of variables can change relative to another. Your experience of time passing could be the result of the complex correlations between the vast number of quantum degrees of freedom in your brain and your environment, all of which are part of the universal foam. One part of the universe acts as a clock for another part. For instance, the regular, predictable emission of photons from a distant pulsar provides a reference against which we can measure other, more complex processes. But at the fundamental level, there is no prime clock. There is only a vast web of interrelated change. The flow of time is the story we tell ourselves to make sense of this endless cascade of correlations within the frozen architecture of the cosmos. It is a story that emerges with such compelling force from the quantum graininess of reality that we cannot help but feel it as the most real thing in our existence, even if it is, at the final count, a magnificent and necessary illusion. If you were to try and measure the position of an electron with ever-increasing precision, plunging down to scales far smaller than an atom, classical physics would suggest that you could, in theory, pinpoint its location with infinite accuracy. You could shrink your measuring device indefinitely, getting closer and closer to an infinitely small point. But this idealized notion runs into a brick wall in the real world of quantum gravity, a wall built directly from the turbulent graininess of the quantum foam. This leads us to a truly fundamental prediction shared by many of the theories we've discussed, the concept of a minimal length. This isn't just a very small distance. It's the absolute smallest possible unit of space that can ever exist, a fundamental limit to how finely we can slice reality. This minimal length is believed to be on the order of the Planck length, a scale so inconceivably tiny that it is to a centimeter what a single centimeter is to the entire observable universe. At this scale, the very idea of here and there begins to dissolve, and distance as a continuous concept ceases to have any meaning. The engine driving this fundamental limit is the quantum foam itself. Remember that seething, probabilistic sea where virtual particles and spacetime itself are in constant, violent fluctuation. That chaotic activity isn't just a feature of the vacuum. It actively prevents you from ever seeing a perfectly smooth, infinitely small point. Imagine trying to measure the surface of a pond with a ruler during a violent storm. The waves and ripples are so large and chaotic that the very concept of the water's surface at a single mathematical point becomes impossible to define. Your ruler is jostled constantly, and any measurement you try to take is overwhelmed by the turbulence. The quantum foam creates a similar, but far more fundamental, kind of turbulence at the Planck scale. The energy required to probe such incredibly small distances is so immense that, according to the Heisenberg uncertainty principle, it would condense into a microscopic black hole, instantly swallowing your hypothetical probe and completely obscuring the measurement. You simply cannot see past the foam. The graininess of this foamy structure means that spacetime is not infinitely divisible. It has a fundamental pixel size, and you cannot resolve anything smaller than that pixel. It's like a digital photograph. You can zoom in only so far before the image breaks down into individual blocky pixels, and you can't see anything smaller than a single pixel. The universe, at its most fundamental level, is pixelated, and the Planck length is the size of that ultimate pixel. This radical idea provides a stunningly elegant solution to one of the most persistent and frustrating problems in all of theoretical physics, the problem of infinities. In our current best theories of particle physics, we treat electrons and quarks as perfect, zero-dimensional points. This mathematical simplification works remarkably well at the energies we can test, but it leads to catastrophic blow-ups when we push the equations to their limits. When you calculate the probability of certain interactions involving these point-like particles, the answers you get are often infinite, nonsensical results that signal a deep flaw in our description. These infinities arise because you're essentially asking the theory what happens when two objects with no size get infinitely close together, a scenario that the real, grainy universe simply doesn't allow. The minimal length imposed by the quantum foam acts as a natural and physical cutoff that prevents these infinities from ever occurring. It's like replacing a perfectly sharp, infinitely thin needle with a ball bearing that has a small but finite radius. The needle can pierce anything with infinite pressure at its tip, leading to mathematical singularities. The ball bearing, however, distributes the force over its surface, and no matter how hard you push, the pressure remains finite. By introducing a fundamental graininess to spacetime, the quantum foam ensures that particles never truly get infinitely close, because infinitely close is a mathematical fiction that has no counterpart in our physical reality. The foam smears out the sharp points, smoothing over the infinities and providing a potential pathway to a complete, finite, and consistent theory of quantum gravity. To make this tangible, consider the famous double-slit experiment, but now imagine performing it with electrons of such incredibly high energy that their quantum wavelength is smaller than the Planck length. In a perfectly smooth, continuous spacetime, these ultra-high-energy electrons should still produce a clean interference pattern. But if spacetime is grainy at the Planck scale, that beautiful pattern should begin to blur and break down. The subtle interference of the electron's probability wave with itself would be disrupted by the bumpy, foamy texture of the spacetime it's traveling through. It would be like trying to create a perfect, coherent laser light show on a screen made of rough, gravelly stone. The fine details of the pattern would be lost in the noise of the underlying texture. While we are astronomically far from being able to perform such an experiment directly, this principle underpins the search for Lorentz invariance violation and energy-dependent photon delays we discussed earlier. The minimal length isn't just a theoretical curiosity. It's a concrete prediction that, if true, must leave some faint, observable signature on the behavior of the most energetic particles in the cosmos, a whisper from the fundamental graininess of existence. Now we turn to a theory so elegant and profound it seems to reconcile two of Einstein's greatest intellectual struggles, a proposal that the two monsters of modern physics, spooky action and gravitational bridges, are, in fact, one and the same. This is the AR equals EPR conjecture, a revolutionary idea that dares to unite the geometry of spacetime with the phenomenon of quantum entanglement through the hidden plumbing of the quantum foam. To grasp its power, we first need to revisit these two classic puzzles. In 1935, Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper highlighting what they saw as a deep flaw in quantum mechanics. They described a thought experiment where two particles become entangled, their fates linked so intimately that measuring one would instantly determine the state of the other. no matter how far apart they were separated. Einstein famously dismissed this spooky action at a distance as an absurdity, believing it violated the cosmic speed limit set by his own theory of relativity. In that very same year, and with the very same colleague Nathan Rosen, Einstein published another paper, this one exploring the solutions to his equations of general relativity. They discovered that the math allowed for the existence of a bridge connecting two distant points in spacetime, a structure we now call an Einstein-Rosen bridge, or more popularly, a wormhole. For decades, these two concepts, EPR entanglement and ER wormholes, were seen as completely separate, even contradictory ideas. One was a bizarre feature of the tiny quantum world that seemed to bypass space. The other was a hypothetical feature of the large-scale gravitational world, a tunnel through space. The ER equals EPR conjecture, championed by physicists like Juan Maldacena and Leonard Susskind, boldly declares that these are not two different things. They are two different descriptions of the exact same underlying physical reality. The conjecture proposes that every single pair of entangled particles, every EPR pair, is not connected by some invisible, spooky influence across a void, but is in fact linked by a microscopic Einstein-Rosen bridge, a tiny wormhole woven from the very fabric of the quantum foam. When you create entanglement between two particles, you are, according to this view, not just creating a quantum link. You are literally stitching a minuscule tunnel in the geometry of spacetime between them. The spooky action is not action across a distance. It is communication through a shortcut, a physical connection that is so incredibly fragile and tiny it exists only at the Planck scale, hidden within the frothing foam. This provides a stunningly concrete, geometric picture for quantum entanglement. The reason entangled particles are perfectly correlated is not because they are sending secret signals faster than light, but because they are essentially two mouths of the same fundamental object, connected by a geometric thread so fine it is invisible to all but the most fundamental probes. So, where does the quantum foam fit into this breathtaking picture? The foam is the dynamic, probabilistic medium from which these ephemeral wormholes are constantly forming and dissolving. The ceaseless churn of virtual particles and fluctuating geometry we've been exploring is not just random noise, it is a seething cauldron of potential connectivity. In this view, every virtual particle pair that blinks into existence is not merely a fleeting energy fluctuation, but could be the signature of a transient, microscopic wormhole forming within the foam. The particle and antiparticle are the two ends of this tiny bridge. Their instantaneous annihilation is the wormhole pinching off and collapsing back into the foamy vacuum. The foam, therefore, is not just empty space. It is a densely interconnected network of these fleeting wormholes, a cosmic subway system of unimaginable complexity where tunnels are constantly being dug and demolished, creating a fundamental, underlying connectivity between every point in space. This has monumental implications for our understanding of black holes and the fate of information. One of the biggest puzzles in theoretical physics is the black hole information paradox. If you throw an encyclopedia into a black hole, does the information it contains vanish forever when the black hole eventually evaporates through Hawking radiation, violating a fundamental law of quantum mechanics? The ER equals EPR conjecture offers a beautifully simple resolution. It suggests that the pairs of Hawking radiation particles emitted by a black hole are not just randomly correlated, they are profoundly entangled with each other. And if ER equals EPR, then that entanglement means they are connected by microscopic wormholes. As the black hole evaporates, these wormholes thread together the outgoing radiation particles, weaving a complex web of connectivity that preserves all the information that ever fell into the black hole. The information isn't lost inside the singularity. It is scrambled and transferred into the intricate pattern of entanglement, the wormhole network between the escaping particles. The interior of the black hole is not a separate place cut off from the universe. It is geometrically connected to the exterior through this vast, hidden tapestry of wormholes. This transforms a black hole from a cosmic prison into a highly connected, scrambled processor of information. To visualize this, imagine space as a vast, calm ocean. On the surface, two buoys might seem entirely separate, isolated by miles of water. But if you could see beneath the waves, you might discover they are actually connected by a complex, shifting network of underwater cables and tunnels. From the surface perspective of quantum field theory, the buoys, our entangled particles, are mysteriously linked by spooky action. From the deeper, geometric perspective of general relativity, they are connected by physical bridges, the wormholes. The quantum foam is the turbulent, hidden depths where these cables are constantly being spliced and severed. This conjecture represents a giant leap towards the holy grail of uniting quantum mechanics with gravity. It tells us that the laws of quantum information and the geometry of spacetime are not just compatible. They are inextricably linked, two different languages describing the same holographic reality. The non-locality of quantum mechanics is not a bug but a feature, a direct consequence of the fact that our universe, at its most fundamental level, is far more interconnected and wormhole-riddled than we ever imagined, with the quantum foam serving as the living, dynamic canvas upon which this profound unity is painted. Of all the mysteries we've encountered, perhaps none is as personally felt as the relentless, one-way flow of time. We remember the past, we anticipate the future, and we are perpetually stuck in a present that seems to be forever slipping away. This is the arrow of time, and its direction from an ordered past to a disordered future is one of the most deeply ingrained features of our reality. But why does time have an arrow at all? The fundamental laws of physics, from Newton's mechanics to quantum electrodynamics, are almost entirely time-symmetric. They work just as well if you run the clock backwards. So what breaks this symmetry and gives time its definitive direction? The answer, surprisingly, may be written in the initial conditions of the universe itself, with the quantum foam playing the starring role. To understand how, we need to delve into the concept of entropy, which is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time, it never decreases. This is why a drop of ink diffuses in a glass of water but never spontaneously reforms into a single drop, and why a shattered glass does not piece itself back together. The universe as a whole is the ultimate isolated system, and its entropy has been increasing since the very beginning. This relentless climb toward higher entropy is what we experience as the arrow of time. The crucial, mind-bending question then becomes, why did the universe start in such an incredibly low entropy state? Why was the past so exceptionally ordered? This is where the quantum foam and its behavior at the moment of the Big Bang enters the picture with a profound proposal. Imagine the very first moment of the cosmos. According to this theory, the quantum foam that constituted the infant universe was in a state of unprecedented simplicity and order. Its structure was incredibly smooth, its fluctuations minimal, and its informational content was at an absolute minimum. It was, in the language of physics, in a state of supremely low entropy. Think of it as a perfectly blank, pristine canvas. There is only one way for a canvas to be perfectly blank and smooth, making it a state of very low entropy. But the moment you begin to paint, the number of possible configurations for the canvas explodes. A single brushstroke can be placed anywhere, in any color, in any direction. The entropy has skyrocketed. The Big Bang was the moment the cosmic brush first touched that pristine, foamy canvas. The initial low-entropy state of the foam was not stable. It was a state of immense potential, poised to explode into complexity. The subsequent expansion and cooling of the universe provided the engine for this transformation, driving the foam from its initial, ordered simplicity toward the complex, turbulent, and high entropy we now associate with the vacuum. The ongoing complexification of the foam's structure is what we perceive as the forward march of time. Every quantum fluctuation that creates a virtual particle pair, every microscopic wormhole that forms and dissolves, every new connection in the spin network, each of these events is a tiny step upward in the universe's total entropy. The foam is not a static backdrop, it is an active, evolving system, and its journey from simplicity to complexity is the very engine of time's arrow. Our own perception of time flowing from past to future is our conscious experience of this universal trend. When you burn a log, you are increasing entropy, converting the ordered structure of wood into the disordered smoke and ash. This process is irreversible because it is part of the universe's relentless drive toward higher entropy, a drive that is fundamentally powered by the evolving dynamics of the spacetime foam at the very foundation of reality. We are carried along on this current of increasing complexity, and we call that current time. This perspective offers a stunningly elegant resolution to the puzzle of time's direction. The arrow of time is not a fundamental law written into the equations of physics. It is an emergent historical phenomenon, a consequence of a very special, low-entropy boundary condition at the beginning of the universe. The reason we don't see broken glasses reassemble is not because the laws of physics forbid it, but because it is an astronomically improbable event that would require reversing the cosmic trend of the foam's complexification that has been underway for 14 billion years. The flow of time is the story of the quantum foam's journey from its primordial order to its ultimate, far-future state of maximum entropy and disorder. In this view, the foam is not just the stage, it is the protagonist in the epic story of cosmic time, and its initial, perfectly ordered state at the Big Bang was the first page from which the entire narrative has since unfolded. But as we've seen, the raw, unbridled energy predicted for the quantum vacuum presents a monumental problem, a value so colossal it threatens to tear apart the very reality it underpins. To resolve this, physicists have proposed a theory of breathtaking mathematical beauty, one that suggests every known particle in the universe has a hidden, shadowy twin. This is supersymmetry, and its implications for the structure of the quantum foam are nothing short of revolutionary. At its heart, supersymmetry is a powerful symmetry that connects the two fundamental classes of particles, fermions, which are the building blocks of matter, like electrons and quarks, and bosons, which are the force carriers, like photons and gluons. This theory posits that for every fermion, there exists a supersymmetric bosonic partner, and for every boson, a supersymmetric fermionic partner. So, alongside the familiar electron, there would be a theoretical selectron, accompanying the photon, a photino. These superpartners are not mere duplicates, they are a fundamental extension of the particle family, and their introduction could bring a profound stability to the frantic chaos of the quantum foam. The mechanism for this stabilization is both elegant and powerful, acting like a cosmic balancing scale. Recall that the vacuum catastrophe arises because we calculate the energy of the foam by summing up the contributions from all the quantum fluctuations of every known field. These contributions are all positive, leading to that unimaginably large and problematic cosmological constant. Supersymmetry introduces a perfect cancellation partner for each of these fluctuations. For every known particle that contributes a positive jitter to the vacuum energy, its superpartner is theorized to contribute an equal but opposite negative jitter. The frantic dance of a virtual electron and positron pair blinking into existence would be perfectly counterbalanced by the dance of a virtual selectron and anti-selectron pair. In a perfectly unbroken supersymmetric universe, this cancellation would be mathematically exact. The wildly positive and wildly negative energy contributions from all these particle superpartner pairs would sum to precisely zero, resulting in a net vacuum energy of zero and a cosmological constant of zero. This would solve the vacuum catastrophe in one masterful stroke, transforming the quantum foam from a violently turbulent sea into a far calmer, more stable medium. The foam would still exist. The probabilistic nature of quantum mechanics ensures that, but its energy fluctuations would be tamed, their ferocious amplitude dialed down to a manageable whisper. Of course, we do not live in a perfectly supersymmetric universe. If we did, we would have detected these superpartner particles long ago, as they would have the same mass as their familiar counterparts. The fact that we haven't observed them tells us that supersymmetry, if it is a law of nature, must be a broken symmetry. This means that while the symmetry existed in the high-energy furnace of the very early universe, it was hidden as the cosmos cooled, causing the superpartners to acquire immensely heavy masses, far beyond what our current particle colliders can directly produce. Yet, this broken symmetry might be the very key to our existence. The cancellation between particles and their superpartners would no longer be perfect, but it could be nearly perfect. The incredibly heavy superpartners would still contribute their negative energy to the vacuum, almost, but not entirely cancelling out the positive energy from the standard particles. This near-perfect cancellation could leave behind just the tiniest, faintest residue of positive vacuum energy, a minuscule leftover that just happens to match the incredibly small value we observe for dark energy. In this view, the gentle acceleration of the universe's expansion isn't driven by a fundamental constant of nature, but is a relic of a broken cosmic symmetry, a fossil from an earlier, more symmetric epoch imprinted onto the structure of the quantum foam. This idea elevates the foam from a background phenomenon to an active archaeological record. The specific, tiny value of the vacuum energy we measure today becomes a clue, a piece of forensic evidence pointing back to the mass scale at which supersymmetry broke in the early universe. By studying the foam's residual energy, we are, in a sense, indirectly weighing these elusive superparticles. The persistent, foamy churn we associate with empty space is no longer just quantum noise. It is the faint, ongoing echo of a grand, hidden symmetry that once governed the cosmos, a symmetry whose delicate breaking left behind just enough energy to gently nudge the galaxies apart and shape the destiny of everything we see. Now, as we peer deeper into the fundamental character of the quantum foam, we encounter a theory that reframes its very essence, suggesting it is not the coldest, most basic state of reality, but is instead warm. This is the idea that the quantum foam is not a zero-point ground state, but a thermal state possessing a distinct, albeit unimaginably low, temperature. To grasp this shift in perspective, consider the difference between absolute silence and a faint, uniform hum. The classical view of the vacuum imagines it as absolute silence, a complete absence of activity at the lowest possible energy. But the quantum foam, with its constant churn, is more like that pervasive hum. This theory proposes that hum is not just quantum noise, it is literal heat. The seething foam is a thermodynamic system in equilibrium, a cosmic bath held at a specific temperature. This temperature is not measured in degrees Celsius or Fahrenheit, but in fractions of a degree above absolute zero, a value likely tied to the fundamental constants of the universe and potentially related to the infamous cosmological constant. In this view, every virtual particle pair that flickers into existence is not merely a fluctuation, but a thermal excitation, a microscopic packet of heat energy being exchanged within the frothy medium of spacetime itself. This thermal nature of the foam leads us directly to the most profound and somber destiny predicted for our cosmos, the heat death of the universe. The second law of thermodynamics tells us that isolated systems inevitably evolve towards a state of maximum entropy, a condition of perfect thermal equilibrium where energy is uniformly distributed and no more work can be extracted. It is the ultimate state of cosmic rest. For over a century, this has been the prevailing forecast for our universe's far future, a time trillions upon trillions of years from now when the last stars have burned out. black holes have evaporated, and all matter has decayed into a thin, lukewarm soup of radiation and fundamental particles, drifting endlessly in an ever-expanding, dark and cold void. The thermal foam theory provides a stunningly concrete endpoint for this process. It suggests that the heat death is not just the universe becoming cold and empty, but rather it is the cosmos settling into its final, stable identity. The universe will not simply fade into a featureless nothingness. It will achieve a specific, definable state, the state of the quantum foam. The faint, persistent thermal hum of the foam is the heat death. It is the ultimate equilibrium, the baseline temperature of existence itself, towards which all the vast and complex structures of the cosmos, galaxies, stars, planets, and life are slowly and irrevocably dissipating their energy. To visualize this, imagine a steaming cup of coffee sitting in a large, cool room. Initially, there is a dramatic temperature difference. The coffee is hot and active, with complex currents and swirls, while the room is calm. Over time, the heat from the coffee flows into the room, warming it slightly as the coffee itself cools. Eventually, both the coffee and the room reach the exact same temperature. The system has reached thermal equilibrium. All the interesting dynamic activity has ceased. No more steam rises, no more currents flow. The energy is still there, but it is now useless, spread out evenly and unable to drive any further change. Our universe is on the same trajectory. The Big Bang was the moment the cosmic coffee was poured, an event of immense energy and fantastically low entropy. For billions of years since, the universe has been that cup of coffee cooling, its energy slowly spreading out and its structure gradually dissolving. The heat death is the moment it finally reaches room temperature, and according to this theory, the room it equilibrates with is the quantum foam. The foam is not just part of the room, it is the room. Its inherent thermal character defines the final, uniform temperature that every last bit of energy in the cosmos will eventually match. This perspective transforms our understanding of the foam's role in the cosmic story. It is not merely a passive stage or a microscopic curiosity. It is the attractor, the ultimate sink towards which all energy flows and into which all information and structure ultimately unravel. The frantic, probabilistic dance of virtual particles is not a sign of vibrant life, but the gentle, ceaseless simmer of a system that has reached its final, stable form. The arrow of time, which we discussed as the drive toward higher entropy, finds its final destination here in the thermal foam. Once the universe has fully equilibrated with this baseline, time, as we understand it through change and causality, may effectively cease to have any meaningful direction. With no energy gradients left to drive processes, with no possibility for further increase in disorder, the relentless forward march of time grinds to a halt. The cosmos becomes a static, eternal, and thermalized foam, a quiet, endless sea of lukewarm quantum fluctuations, holding in its uniform embrace the faded, scrambled memory of all that ever was. Building on our journey through the thermal destiny of the cosmos, we arrive at a theory that offers a tangible, thrilling possibility, that we may soon be able to directly witness the quantum foam not just in theory, but in the very ripples of spacetime that wash over our planet. This is the bold proposal that next-generation gravitational wave observatories could be tuned to listen for the faint, fundamental hiss of spacetime's foamy texture. Gravitational waves, those majestic ripples in the fabric of reality caused by the most violent cosmic events, have already opened a new window on the universe. But what if these waves carry more than just the signature of colliding black holes? What if, on their billion-year journeys, they also pick up a subtle, statistical noise from interacting with the turbulent quantum foam structure of spacetime itself? The idea is that as a gravitational wave propagates, its oscillating stretch and squeeze of spacetime is not happening across a perfectly smooth, continuous medium. It is traversing a grainy, probabilistic froth. On the most minute scales, the foam's chaotic fluctuations, the constant blinking of virtual wormholes, and the shifting geometry would impose a tiny, random jitter on the passing wave. It's akin to the way light passing through a hazy atmosphere can become slightly scattered, causing a distant star to twinkle. The gravitational wave would not travel in a perfectly pure, sinusoidal form. Its phase and amplitude would be subtly perturbed by this underlying spacetime noise. For our current detectors like LIGO and Virgo, this effect is far too small to notice, completely drowned out by the immense signal from the cosmic collisions and the instrumental noise of the detectors themselves. The predicted jitter from the foam is on a scale quintillions of times smaller than what these instruments can currently resolve. But the next generation of observatories, projects like the Laser Interferometer Space Antenna, or LISA, which will consist of 3 spacecraft millions of kilometers apart, and the Einstein Telescope, a proposed underground observatory with vastly improved sensitivity, are being designed to listen to the universe with ears of unprecedented acuity. These observatories will probe a lower frequency band of gravitational waves, a regime where the cumulative effect of the foam's noise over the wave's incredibly long wavelength could, in principle, become detectable. It's the difference between listening for a whisper in a quiet library versus trying to hear it in the middle of a rock concert. These new detectors will provide the sensitive, quiet environment needed to hear the faintest cosmic sounds. To understand how this detection might work, imagine a perfectly smooth, laser-straight beam of light traveling across interstellar space. Now, imagine that space itself has a fine, sandy texture. The light beam, over a long enough distance, would be ever so slightly deflected and scattered by the individual grains of sand, causing its path to develop a faint statistical wobble. In the same way, a gravitational wave with a wavelength of hundreds of thousands of kilometers, like those from supermassive black hole binaries that LISA is designed to detect, would be sensitive to the graininess of spacetime at the Planck scale. Over its vast journey, the wave would interact with countless individual atoms of space, and these myriad tiny interactions would collectively imprint a characteristic scrambling on the wave's signal. This wouldn't look like a dramatic distortion, but more like a fundamental limit to the coherence of the wave. When physicists analyze the signal, they would find that its phase cannot be tracked with infinite precision, no matter how good their equipment. There would be an irreducible, non-random fuzziness in the data, a subtle hash that doesn't fit the prediction of a wave traveling through a perfectly smooth continuum. This spacetime noise would be a unique signature, one that cannot be explained by any known astrophysical source or instrumental imperfection. Its statistical properties would be a direct fingerprint of the underlying discrete structure of reality, potentially revealing whether the foam is best described by the spin networks of loop quantum gravity, the non-commutative fuzz of other theories, or something entirely new. The analysis would be a monumental feat of data science, akin to identifying a single, specific instrument's hum within the roar of a full symphony orchestra. Scientists would compare the incredibly clean, theoretical templates of gravitational waveforms calculated using the smooth geometry of general relativity with the actual, messy data received by the detectors. Any persistent, statistically significant deviation that aligns with the predictions of a particular quantum foam model would be a smoking gun. It would be direct, observational evidence that spacetime is not a continuum, but is instead composed of fundamental, vibrating units. This wouldn't just confirm a long-held theoretical suspicion, it would open up an entirely new field of experimental quantum gravity. By studying the precise nature of this spacetime noise, its frequency dependence, its amplitude, its correlation properties, we could begin to do spectroscopy on the foam itself. We could measure the effective size of the spacetime quanta and probe the specific algebraic relationships that govern their behavior. This turns gravitational wave astronomy from a tool for studying massive astrophysical objects into the most powerful microscope ever conceived, one capable of peering directly into the hidden, granular foundation of the cosmos. The gentle whispers of distant black holes would thus carry encoded within them the deepest secret of the universe, revealing that the stage upon which their cosmic dance plays out is a dynamic, pixelated tapestry, forever buzzing with the quiet, fundamental energy of creation. After exploring the potential for gravitational wave observatories to detect the faint signature of the foam, we arrive at the final and perhaps most personally resonant of our 30 theories, one that pushes beyond the equations and into the realm of meaning itself. We've journeyed through a universe built from wormholes, holograms, and computational codes, all emerging from a seething, foundational froth. But if we accept that this turbulent, probabilistic foam is the true bedrock of reality, we are forced to confront staggering philosophical questions that challenge our deepest assumptions about existence, consciousness, and our place within it all. The first and perhaps most unsettling implication strikes at the heart of classical determinism, the idea that the future is an unbroken chain of cause and effect, preordained from the moment of the Big Bang. In a clockwork universe governed by strict Newtonian laws, free will can feel like an illusion, but the quantum foam presents a universe that is fundamentally indeterminate. At the Planck scale, events are not determined with certainty, they are governed by probability. The spontaneous creation of a virtual particle pair, the formation of a microscopic wormhole, these are not events caused by prior, local conditions in a strict billiard ball sense. They are random, acausal fluctuations. This intrinsic randomness, woven into the fabric of spacetime, suggests that the universe is not a predetermined tape playing out. There is genuine novelty and unpredictability built into the laws of physics at the most basic level. This doesn't prove free will, of course, but it does dismantle the argument that a deterministic physical law forbids it. It opens a door, suggesting that the universe at large might possess an inherent openness, a capacity for genuine creation that could, in some complex and poorly understood way, be reflected in the conscious choices of sentient beings within it. We are not passengers on a train running on a fixed track. We are navigating a vast, bubbling ocean where the very waves are born from chance. This leads us directly to one of the most mind-bending interpretations of quantum mechanics, one that finds a natural home in the foamy cosmos, the participatory universe. This idea, powerfully advocated by physicist John Archibald Wheeler, proposes that observers are not passive witnesses to a pre-existing reality, but active participants in bringing that reality into being. Wheeler's famous delayed choice experiment illustrates this with stunning elegance. Imagine a particle like a photon traveling through a cosmic version of the double-slit experiment. We can set up our equipment to measure which path it took, forcing it to behave like a particle, or we can set it up to measure its wave-like interference pattern. Astonishingly, the decision of which measurement to make after the photon has already completed most of its journey seems to retroactively determine how it behaved at the beginning. It's as if the universe waits for an observation before settling on a definite history. Now connect this to the quantum foam. The foam is a superposition of all possible geometries, all potential fluctuations. It is a realm of pure potentiality, an observation, the interaction of a measuring device, or perhaps even a conscious awareness, could be the very trigger that forces a particular configuration of the foam to actualize, to transition from a cloud of maybes into a concrete "this happened." In this view, the universe only becomes concrete and definite when it is observed. The ceaseless churn of the foam is the universe in its unobserved potential state, and we, as collections of quantum systems interacting with other quantum systems, are the mechanisms by which the universe crystallizes itself into a specific reality. This is not to say we create reality with our thoughts in a simplistic, magical sense. Rather, through the physical process of quantum decoherence, where a system interacts with its environment, we are all constantly participating in an unimaginably vast collaborative process of reality building, solidifying the foamy probabilities into the shared classical world we all experience. This participatory role forces us to reconsider the very nature of existence. If reality is fundamentally fuzzy and observer-dependent at its core, then what we call the real world is not an absolute objective stage. It is a kind of consensus reality, an emergent approximation that holds together on human scales but dissolves into a storm of probabilities at the foundations. The ancient philosophical question of whether a tree falling in a forest makes a sound if no one is there to hear it takes on a new quantum mechanical dimension. In a universe with a quantum foam, the tree, the forest, and the sound are all ultimately composed of quantum fields. In the absence of any interaction that causes decoherence, one could argue that the event exists only as a superposition of possibilities within the foam, a potential falling, a potential sound. It is the interaction with the environment, the air molecules being disturbed, the vibration of the ground, that constitutes a form of continuous observation, collapsing this potential into a definite occurrence. This line of thinking elevates the concept of relationship to a fundamental principle. Things do not exist in isolation with definite properties. They exist in relation to other things, and their properties are defined through interaction. The universe isn't a collection of independent objects, but a vast, dynamic web of relationships, and the quantum foam is the physical manifestation of that web's probabilistic, unmanifested state. It is the canvas of pure potential from which all specific relations and entities emerge. Ultimately, the existence of the quantum foam invites a profound sense of humility and wonder. For centuries, humanity has sought to uncover the ultimate, simple laws governing the cosmos, hoping to find a pristine, mathematical elegance at the bottom of it all. Instead, we may have found a roiling, chaotic, and creative chaos. The foam suggests that the universe is not a perfectly engineered machine, but a living, breathing, and spontaneous process. It is a system that creates itself from moment to moment, not according to a rigid, deterministic plan, but through a dynamic dance of probability and actualization. This view connects us intimately to the cosmos in a new way. We are not insignificant specks on a tiny rock in a vast, cold, and indifferent universe. We are inseparable from the universe's own process of self-creation. The same foamy turbulence that births virtual particles and weaves the fabric of space also fires the neurons in our brains, driving our curiosity to understand it. Our quest to comprehend the quantum foam is the universe, in a very real sense, beginning to comprehend itself. It is a reminder that we are not just in the universe is in us, and our journey to understand its deepest nature is the most thrilling and meaningful adventure we can possibly undertake. And so, we find ourselves at the end of our wild expedition, having navigated the turbulent, mind-bending seas of the quantum foam. From its foundational churn where spacetime itself boils with virtual particles, we journeyed through wormholes linking entangled particles, explored a universe that might be a holographic projection, and confronted the immense mystery of the vacuum-catastrophe. We saw how this foam could be the atomic weave of loop quantum gravity, the causal network of a deeper reality, and even the engine behind the universe's accelerating expansion. We considered the possibility that it's a thermal state leading to cosmic heat death, a superfluid medium from which gravity emerges, and a quantum error correcting code protecting the very information of reality. We've wrestled with timelessness, minimal lengths, and the profound idea that our observations might participate in bringing this foamy potential into concrete existence. This has been more than a tour of 30 theories. It has been a descent into the fundamental substrate of everything, revealing a cosmos far stranger and more interconnected than we ever could have imagined from our classical, human-scale perspective. This incredible journey underscores one undeniable truth: the quantum foam is the final frontier of our current understanding. It is the jagged edge of the map, the place where the reliable laws of general relativity and quantum mechanics both break down, screaming for a new, unifying theory. The foam isn't just another puzzle in physics. It is the central mystery, the common ground where the impossibly small meets the unimaginably large. Every theory we've explored, from the radical proposals of pregeometry to the elegant conjectures like ER equals EPR, represents a different path through this uncharted territory. The sheer diversity of these ideas, from the mathematically rigorous to the philosophically profound, tells us that we are in a period of explosive creativity and deep uncertainty. The next great revolution in physics will not come from simply refining what we already know. It will erupt from a fundamental insight into the nature of this foamy foundation, finally revealing whether spacetime is discrete or continuous, whether it is fundamental or emergent, and how information, causality, and geometry are ultimately woven together into the single tapestry we call reality. The adventure doesn't end here. In many ways, it is just beginning. New experiments, from next-generation gravitational wave observatories to ultra-precise tabletop measurements of gravity, are being designed to listen for the faint whispers of this spacetime foam. The data we gather in the coming decades may finally allow us to distinguish between these competing visions, to move from philosophical speculation to empirical fact. This is one of the most thrilling aspects of modern science. We are on the cusp of potentially answering questions that have haunted physicists and philosophers for a century. What is space? What is time? And what is the true nature of the vacuum from which we all emerged? The quantum foam holds the key, and we are steadily, inexorably learning how to turn it. Now we turn the conversation over to you. After this epic journey through 30 of the most incredible ideas about our universe, which one truly reshaped your understanding of reality? Was it the holographic principle, suggesting we might all be projections on a cosmic screen? The stunning ER equals EPR idea, merging wormholes with quantum entanglement, or perhaps the humbling concept that the entire cosmic web of galaxies originated from microscopic quantum jitters? Let us know in the comments below which theory blew your mind the most. We read every single one and love continuing the discussion with this incredible community. If you enjoyed this deep dive into the universe's greatest mysteries, make sure to subscribe and hit the notification bell. We have so many more frontiers to explore together, from the enigmas of dark matter and dark energy to the search for life beyond Earth. Thank you for joining